Test. Okay. Greetings, everyone! Welcome to the magical session, Right, Reading and Writing Tools. My name is Ruofei Du, and I lead research and development in interactive perception and graphics at Google. Today, we are going to watch amazing talks in reading and writing tools. And each talk will last about 8 minutes, and we have 4 minutes for Q&A. Our first talk is presented by Professor Jeffrey Heer. Jeffrey Heer is a Jerry D. Nord Professor of Computer Science and Engineering at the University of Washington, where he directs the Interactive Data Lab. And his talk is entitled Living Papers, a language toolkit for augmented scholarly communication. This paper won the Best Paper Honorable Mention Award at UIST 2023. And congratulations.
Thank you.
Yeah, thank you. All right, again, welcome to the magical session, Right. Let the show begin with a round of applause.
Okay. All right, can you hear me all right? Yep, wonderful. Hello, good morning. Thank you for joining us bright and early at 9 a.m. And so Living Papers is a language toolkit for authoring interactive web articles, static LaTeX PDF documents, and information extraction APIs, all from a single source document. And though computing has deeply shaped how academic articles are produced, article formats and affordances have changed little over centuries. And while physical paper has virtues as a format, academic articles are now often read on a screen in a format that lacks interaction, raises accessibility concerns, and complicates computational extraction and reuse. So, in addition to print-optimized output, Living Papers provides web-based output, complete with a reactive runtime and built-in reading augmentations, including contextual previews for bibliographic citations and internal cross-references. Here we use Living Papers to recreate a classic paper on optical flow estimation. Augmented math formulas include colored terms, with term definitions available upon click. So we scroll down, we'll see that the article also includes margin figures, here placed adjacent to related content. And as needed, these figures can be made persistent to stay visible and maintain context across relevant passages. From that same source document, Living Papers also generates LaTeX projects and PDFs, aligning incentives through participation in existing publication workflows. And the interactive elements here are automatically converted into static, print-compatible content. Living Papers includes a reactive runtime, enabling interactive articles, such as this explorable multiverse analysis. Here, interactive text enables the reader to assess the effects of a variety of different data analysis decisions. The reactive runtime and an extensible component system allow authors to orchestrate interactive figures. This article describes the Barnes-Hut approximation for n-body forces. Linking among input elements, plots, and text enables readers to explore algorithm parameters and assess their effects on algorithm performance. So for example, here we can update parameters via linked text and figures. Living Papers can also support alternative reading interfaces. Here, Living Papers web content populates a zoomable canvas. Readers may click a column and here enter a linear reading mode. Scrolling past the end of the column then pans the view over to the next column. And meanwhile, interactive content and reading aids will remain accessible. Living Papers uses an extended Markdown syntax for article authoring. Both built-in and custom components can be defined within article text. Bibliographic citations can refer to provided BibTeX entries or be automatically resolved from provided digital object identifiers. And then JavaScript code blocks and dynamic component parameters define reactive variables and orchestrate interactive updates. So to further break it down, example elements may include JavaScript code blocks evaluated reactively, interactive components, and dynamic typeset math, which here actually produce this interactive figure and caption. Again, Markdown is used to format body text, while here below we have another code block, but this time importing a visualization that was defined externally in an observable notebook. So given these source documents, the Living Papers compiler parses the input to form an initial abstract syntax tree. AST transforms, including code extraction and citation processing, produce a canonical document model. So for example, the optional knitter transform actually evaluates our code at compile time and then stitches the results back into the AST, similar to R Markdown, if you know that. And meanwhile, the pyodide transform identifies executable Python code, which is now evaluated live in the browser as part of the Living Papers reactive runtime. Once this canonical AST is ready, modules for HTML, LaTeX, and API output apply their own output-specific transforms. So for example, converting dynamic content to static assets when needed. The output modules then perform code generation to produce static PDFs, interactive web pages, and APIs for content extraction and reuse. API output produces a JavaScript module for programmatic access to all paper content, including pre-rendered images of numbered figures, tables, and equations. Interactive content from the reactive runtime is also compiled to an external module, enabling import and reuse. You can actually import figures from one paper into another. And so we believe that publishing tools should support both people and machines to better make sense of and build upon the research literature. And to date, we've used Living Papers to write multiple published articles, including, of course, the Living Papers WIST submission itself, but also papers at IEEE Viz, and Josh's work on ngraph, which you should definitely come check out this afternoon. The various features we've seen so far, such as supporting interactive articles alongside standard print workflows, actually stem from a set of sometimes competing design goals. And these goals were shaped in discussions with stakeholder groups, such as researchers of augmented reading, accessibility, and information extraction, also with developers of many different publishing tools, and with a set of graduate students in a course on the future of scholarly communication we held at UW. And if you're interested in the readings, you can get the link here. And more broadly, I think this is a really compelling, exciting area for continued research. So in terms of future work, a large class of both readers and writers could benefit from a standard toolkit of reading augmentations that can be deployed with little to no effort and ranging across citations, definitions, equations, figures, and more. And while there's already a lot of promising prior work in this space, there also remains a large and exciting design space for us to better characterize and, most importantly, to also evaluate. One next step for Living Papers itself is to better support collaborative editing and reviewing, and I'm particularly interested in how computational document formats might better enable richer reviewing experiences, both pre- and post-publication. And we should also revisit various tensions amongst those design goals I briefly showed earlier, particularly between dynamic content on the one hand and accessibility on the other. So for example, how might we effectively convert dynamic content to similarly informative static content? Living Papers includes basic conversions akin to screenshots, but future work might convert videos or interactive figures, for example, to multi-panel comics and captions for different forms of communication. And so for more, we encourage you to interact with our supplemental materials, which includes an interactive web version of our WIST submission. And in sum, Living Papers provides a language toolkit consisting of a standardized model for augmented interactive documents, along with a set of extensible parsers, AST transforms, and output generators. Living Papers is available as open source software intended to support both authors and researchers of augmented reading and writing experiences. And so if you're interested in building on this framework in your own work, please reach out. We'd love to collaborate. Thanks.
Thank you, Professor Here and your team for the amazing talk in Living Papers. Any questions from the audience are welcome.
Hi, thank you for a very great question, great talk. And I'm Jotaro from Sony R&D, and I have a question. I'm new to the field, but I have a question about the code maintainability for the interactive documents. So basically, I see a lot of code go deprecated, and see a lot of interactive elements go deprecated. Like over time, the framework evolves, and I just wanted to hear about your thoughts on how to sustain the framework.
Okay, so the question is about sustainability and code deprecation. There's a couple different aspects to it. So one is just in general archivability. And so there's two different things that we've thought about here. So one, of course, is this conversion to paper and static assets. Paper actually preserves over centuries so far better than bits on a hard drive. So that's one piece of the puzzle. The other is there's also web archival formats that are an important piece here. There's also the question about just the sustainability or how the language of living papers itself might change over time. That's a great question. I mean, one of the things that we've intentionally chosen to do is to embrace the web and web standards, and there will be, in my opinion, enough important efforts to preserve web content over time that hopefully that we can draft on that as well, as opposed to an idiosyncratic, self-designed language that is less likely to have that feature. And so I think the issue still is a real one to consider, but those are some of the ways in which we've thought about that problem. Yeah, thanks.
Hi, great paper. I'm Brandel Zachernak, Immersive Web Standards at Apple. I'm wondering, have you looked at augmenting into augmented reality and this spatial representation of papers based on the semantic understanding you have from this?
In all honesty, the short answer is no. And I would love to chat about that more if you have interesting ideas where our work might be helpful or informative for you.
Yes.
Yeah, thanks for the question. Yeah.
Question?
Hi, Michel Baudouin-Lafont, Université Paris-Saclay. Great job and great work. The question I have is, what is the authoring side of this? Because
Yes.
there's a compiler, so does this mean if you author one of these interactive figures, you have to write stuff and then compile, wait, and see what happens, and then how does this work?
Yeah, so we tried not to boil the ocean. You noticed there was already a lot in there. And very much so, and we'll talk a little bit about this in the paper, that both different types of editing interfaces and the exploration of those, as well as the different collaboration features I alluded to earlier, I think are exciting next steps. In prior work with Matt Conlon, who was a co-author on this, he also wrote Idle, which was a big inspiration and starting point for this work. We also had at UIST this paper Idle Studio, which was a WYSIWYG editor for interactive articles. And so we think some of those ideas and approaches might be applicable here as well. We just haven't had the time and resources to get to that yet. But I think it would be I think a necessary thing, particularly if we want to reach out of science and engineering to a broader class of authors. I think that would be particularly important.
And how does it scale? Like if I'm writing an entire textbook instead of an article?
Similar to web pages or LaTeX. Ultimately, there's the authoring process, but there aren't any major computational bottlenecks. Depending on what transforms you're running at compile time, of course, you might have some varied running times, but we're talking on the order of seconds as opposed to minutes or something else. And then, sort of similarly for books, you break down into chapters. There's some very natural subdivisions that apply just as well here as they do in other forms of authoring.
Okay, thank you.
Yeah, thanks.
Yeah, thank you, Professor Kier. And let's give another round of applause to the authors. Thank you.
Thank you.
All right, our next speaker is Hyun-Soo Kang, a CS PhD candidate at the Carnegie Mellon University, advised by Professor Nikki Kitter. He's in the academic and the industry job market this year. And his website is hyunsookang.com, and for more information. His talk is entitled Synergy, a mixed initiative system for scholarly synthesis and sense-making. Let's welcome Hyun-Soo Kang. All right.
All right. Thank you for the introduction. My name is Hyun-Soo Kang, and today I'll be presenting our work on Synergy, a mixed initiative system for scholarly synthesis and sense-making. This was a collaborative project with Sherry Tongsheng Wu and Nikki Kitor at CMU-HCII and Joseph Chi Chang at Allen Institute for Artificial Intelligence. So to motivate this research, Isaac Newton famously said, "Stand on the shoulders of giants," to emphasize the importance of pre-existing synthesis of knowledge for making new challenges tractable in a single human's brain. Newton himself learned partial abstractions from Ptolemy, Copernicus, Kepler, Galileo, as well as the Descartes' analytic paradigm, which he used as foundations to his calculus problem. However, as knowledge accumulates, the following generations face an increasing burden of education. Here, Jones shows that the age of first innovation from patent data is increasing over time, and similarly does the age of notable achievements. And truly, the immense scale of accumulated knowledge really makes us feel like looking for a needle in a haystack when conducting literature reviews for fresh insights. Zooming into scholarly synthesis in particular, we see that scientists build up threads of research while reading, identifying high and low level interesting research threads from the text, but oftentimes it feels like one needs to fight through dense scholarly text to piece together the golden insights. Descriptions of research threads are scattered within many pages of a single paper and across multiple relevant papers, and they are also interleaved with references pointing to the sources outside the papers scholars are reading. So the high-level goal of this research is to help address these challenges by developing a new tool that helps people synthesize from prior knowledge more effectively and discover related work along the dimensions of their synthesis. We situate this systems research in a spectrum of how much of the user initiative is automated into workflow design between the bottom-up and top-down ends. Systems like Thready and Apollo help scholars explore the literature in a bottom-up manual process, which is helpful for learning by doing, but suffers from the recursively accumulating context and the cognitive and context-switching costs. On the other end of the spectrum, systems like Galactica and Metromaps help scholars by providing an initial overview structure which help them preview the global research space, but often their outputs are too complete for iteration and may require manual verification and error fixing. So here we instead propose a mixed initiative system by augmenting a bottom-up workflow based on Thready with AI that can expand user-provided research threads on demand using citation graphs and LLMs. By doing so, Synergy helps scholars move between the bottom-up and top-down process and combine benefits from both. So here's a quick demo of Synergy in action. So the user is starting from one paper on a topic, then finds an interesting research thread that is described in the paper PDF, which she highlights and saves to the system. And Synergy provides additional related research threads and notable papers in the broader research area for her to continue on the literature review on the topic. So to go over the step-by-step Synergy workflow, first the user opens up a research article PDF on a Synergy installed web browser. Then she finds an interesting clip of text describing a notable thread of research with citation context and references which she highlights and saves. Then Synergy uses the user-specified input clip as a seed for expanding on the review in the neighborhood of related literature. She can switch to the editor view to see Synergy-generated threads of research in closely related research neighborhoods, which she can import via drag and drop or modify as needed. Synergy also provides rich details for each thread, including an automatically generated heading of notable research threads and citation context that support them. In addition, Synergy provides tooltip features for at-a-glance information of paper details in each citation context, or the other way around, so different citation contexts that show how each paper was cited in a manner that is specifically related to the user input. The design choice for Synergy, supporting direct highlighting in a paper PDF, builds on our prior work, Thready, which we presented at UIST last year. To briefly provide context for this, Thready aimed to augment scientists' flow of reading for more effective synthesis, specifically by helping them systematically reuse other scholars' synthesis. The challenges that Thready aimed to address were reducing multiple kinds of cognitive and context-switching costs associated with this type of reuse. So for example, there are several manual subtasks that scholars have to do, such as looking up the references in the bibliography of a paper, finding their details, then saving them into a reference manager along with saving useful clippings of the context from the text. These subtasks would then need to be repeated for each citation, a thread, and a thread in a paper. The scientists will also need to organize the threads into a larger structure. In the example shown here, nesting, cross-referencing, and in situ summaries under augmented reading. So it's easy to see how these would really add up to the demand of the task that's already there. So Thready helps with these. But there are remaining challenges with Thready's design, most notably that the manual bottom-up nature of Thready interaction means users are still required to manually process entire documents, and they cannot easily get a sense of related papers, relevant research threads in them, and the overall structure among those threads. So the goals for Synergy's features focused on addressing these remaining challenges. assisting users' processing by extracting notable threads based on user input, pre-digesting pre-digesting other related papers along the user input, etc. So we enable this in Synergy architecture by developing an algorithm that uses the citation context that describes how the included references are related, as well as the references themselves to search for other related papers. Here, the references 34, 20, and 16 are used as seeds of exploration, as you can see on the right, where we perform a two-hop citation neighborhood construction for each paper. We store the citation context text that describes how each paper in the neighborhood was referred to as annotations for each edge in the neighborhood graph, which we use to prioritize papers that have been referred to in similar ways before as the user input through similarity weighting in belief propagation. In this sense, a thread with its rich citation context, description, and a set of references acts as kind of a boundary object that translates the user's literature review intent to AI. After papers related to the user entrusted citation context are found, Synergy retrieves the full PDF, paper PDF text from the web and parses that. Synergy filters most relevant clips of text and references within them, and finally, using the newly found clips, Synergy hierarchically summarizes them into a three-level structure, which is presented in the interface for user to review and modify. So to evaluate Synergy's usefulness, we ran a within-subject lab study with 12 scientists and 2 domain experts where we asked them to review the literature on predefined topics to create a reusable literature review outline. We found that users felt that Synergy-generated initial structures were useful in ways that helped them visualize the review outline and think at a higher level about different threads of research that would go into their review structure and divide the related research space. Interestingly, when domain experts reviewed the helpfulness of user-produced outlines, they found that the Synergy conditions showed the highest overall helpfulness of review outlines, higher than GPT-4 generated outlines, and outlines generated by human users in the thready condition. In particular, Synergy helped users collect more evidence from related literature, which increased the helpfulness of the outlines. Finally, we also found from user behavioral traces that Synergy supported the bottom-up process, where users started by importing system-generated threads, clips, and their references into the editor and organizing that. Synergy also supported top-down process, where users started by creating placeholder for salient threads about a topic in the editor and importing relevant subthreads from the system-generated structure. The latter seemed to be the case when the user was more knowledgeable about a particular domain, so they could cold recall important threads of research when prompted. You can find more details about the findings in the paper. So we believe there's a large design space for future work in this area, and I'll end with 4 dimensions along abstracting and discovering, pre-digesting, and prioritizing, extracting, and synthesizing output that is rendered much more alive than what is currently available as areas for future research. Thank you.
We have 2 questions. Yeah, thank you.
Hello, I'm Aaron Quigley. I'm from Australia's National Science Agency. I was just wondering, have you thought about using this to help people understand the author's intent in 2 ways? One, what I call the Princess Bride problem, which is people using words that they think mean one thing but actually mean something fundamentally different. But also people who you feel when you're reading the paper didn't actually read the cited work. I've been doing all my Chi reviews recently and reading through some of the citations. People cite work, and I know the work. I'm like, you've cited the work, but I don't actually think you've read the work. I don't think you know what you're citing. So is there any way to kind of take what somebody has said and use it as a lens to look into the paper, the other paper, and go, where in that other paper does this magical, non-existent concept actually exist? Because people just cite to the paper without actually pointing to a specific substrate. Bring it in and go, oh, actually, yeah, that is actually, conceptually is in that paper, rather than just nonsense and is a random reference. Could I do that with this system?
Short answer, right now, I think it falls short of supporting that fully, but I can see that there are 2 aspects. One is kind of detecting the reader's mental state or levels of knowledge in that area to know which terms or rich concepts need kind of scaffolding in the paper while they are reading the paper. And the other side is the author's intent. No paper exists in a vacuum. It's like rarely the case that it starts from absolute bare minimum scratch, right? And so it comes with the baggage, not baggage, but the trail of depth of knowledge that actually that the new work is building upon. So I think I can see opportunities where we can look at the author's previous publications in that area, or like you mentioned, the cited works, like kind of maybe synthesizing and summarizing more specifically about the particular area, a concept or phrase or terms that the reader is confused about, to kind of help them understand the context as well as the depth better. So I think that's a fascinating area for future research.
Good job. Very nice work. Thank you.
Yeah, last question.
Hi, I'm Hitha from the University of Pennsylvania. This is a really great talk and a really compelling motivation. I wonder if when developing Synergy, the goal was to reduce the actual number of documents that people had to read, and was that something that came up in the evaluation?
It was part of the goal. I mean, no one really has the time. I feel like bandwidth of attention these days are getting lower and lower by day. So we wanted to reduce the raw amount of text, or maybe kind of trade that off with getting the gist or getting to the meaty parts of the paper faster. So that was one part of it, but we cannot absolutely get rid of, because there's definitely a certain value of reading the raw material yourself and digesting it yourself. Especially when you're kind of maybe newcomer to an area that's particularly could be helpful for your learning and self-actualization. And so there's a fine balance, I think, between the two to trade off how much of the reading that you, as a reader, actually have to do to get the base level of understanding to then maybe go to more efficiently process subsequent papers that you're going to be reading in the future. So yeah, great question.
Thank you. Let's give the authors another round of applause. Our next speaker is Zhen Huipeng. Zhen Huipeng is an assistant professor at San Yat-sen University in China, and his talk is entitled Crit Trainer, an adaptive training tool for critical paper reading. Let's welcome Zhen Hui.
Yeah.
Try another one. Did you try the? Yeah. Can SV come here to help? Yeah.
Yeah, it should be okay. It should be okay now. Yeah, it should come up. It should come up.
All right. All right, let the show begin.
Okay, good morning. I'm Zhen Huipeng from Sun Yat-sen University in China. I represent my students Kang Yu, He Hai, Si Lei, and my co-authors Qin Yu and Dr. Xiaojuan Ma to present this paper, Crit Trainer, an adaptive training tool for critical paper reading. So reading scientific papers critically is a basic skill for our researchers, and it requires us to comprehend the main ideas, including the paper's background, motivation, methods, and also we may take skeptical views, and such as whether the claims are reasonable and why the alternative approach are not chosen. So the critical paper reading skill can be reflected on their performance or users' performance in summarize the paper content. It's like we are writing a review. We should summarize the paper content first and raise some critical thoughts on this paper. So how do we normally run critical paper reading? We can refer to the online critical paper reading guidelines. The good thing is they are always there, but they are quite general and they are not adapted to the paper content. And we can get support from the course instructors, peers, and senior researchers, or get questions from all of you. But this kind of support, these questions is specific, but these scenarios, these persons, they are not always there. So is there a solution that can always offer adaptive running support? We actually got inspired from work on reading support tools like my previous work, Clipboard, and the reading paper or Synagic, just shared by the other two authors. Okay. And we also get inspired by the Malvista that will be shared in the later in this session. But we differ from this tool as we positioning QuickTrainer as a training tool. The goal is to enable independent critical paper reading after the training session without AI support. So we also got inspired from work on intelligent tutoring tools like Quizbox and ArgueTutor. And we follow these tools to offer adaptive support and feedback in a structured running process. So our proposed work, we propose a QuickTrainer, and we first structure a structured training process. And in this process, we conduct a formative survey study to identify user challenges and their needs for support. And we developed a template-based approach to generate critical thinking questions. And we currently develop QuickTrainer as an add-on to the Google Doc. And finally, we conduct a mixed design user study and offer some design consideration. So here is our critical paper reading training process. In this process, users should first read papers with questions in mind, and then they need to conduct the first task, a summarization task. They need to summarize the content of a paper session, and then check the feedback from the AI. And the next task is to raise some critical thinking questions on the reading content and try to improve their questions. And we conduct a survey study with potential users to identify user challenges and also their needs for support in this process. We ask them to rate the perceived usefulness of these features based on by our research team, and we implement the ones with the top ratings. Here is the overview of the adaptive support from QuickTrainer in the training process. Let's look at it in detail. First, in the QR stage, the QuickTrainer will generate comprehension questions about the theoretic session, like the introduction session, the related work sessions, and try to guide the users to read, to understand the paper session first. And then in the first AC stage, the users should try to write a summary by themselves first about, write 2 or 3 sentences to summarize these paper sessions, and then when they click submit, they can get feedback. Actually, the feedback is an AI-generated summary for them to reference. They can see the highlight points that compose this summary and check, try to understand how to write a summary, how to understand the paper. And then in the second AC stage, the users can click some detect keywords and check the template and try to raise some text-specific critical thinking questions. And if they don't know how to do that, they can get hints that which will get some generated text-specific questions and use them as the reference. So to generate critical thinking questions, we develop templates filled by 3 types of keywords: method, background, and results. We first use sentence classification model to track on the abstract data to classify sentence in a session into 3 types, and use the keyword extraction model to identify the keywords. And we conduct a mixed design user study to evaluate our proposed QuickTrainer. The study procedure is on day 1, the users will take a pretest without any support. We just give the user a paper and they read it and try to summarize it and try to raise critical thinking questions. Then on the day 2, they have the training session with either the QuickTrainer or a baseline tool without the text-specific and interaction features. And then after the training sessions, they have a post-test. They need to read another paper without any support, without the QuickTrainer, without without the baseline tool and write a summary again, raise critical thinking questions. And we try to evaluate the performance before and after the training session. And we found that the key findings, okay, after training with either tool, participants can better express their understanding of the paper content in their draft summaries. We also found that the participants with Crit Trainer have significantly more improvement regarding their ability to raise understandable, relevant, and critical questions after the training sessions. Participants highlight the benefits of the Crit Trainer's test-specific questions. And our work actually provides evidence to the importance of specific guidance in developing critical thinking skills. There's no benefit of Crit Trainer over the baseline on improving performance in summarization paper content. We think that this is, we provide highlighted key points, but participants may spend less effort in thinking about how to capture the key points and write them down. And our tool can also be used to train users' critical thinking skills in other scenarios and also help them to self-check their paper draft, paper reviews. So here are some design considerations. Based on our finding, the one point I want to emphasize is the training tool should encourage necessary effort spent in the running task. Okay, for future work, we think one important point is we should develop autometrics for critical paper reading skills. Currently, we just manually measure their paper reading skill, but if we have autometric, we can provide feedback on the users. Okay, in summary, we present an adapted critical paper reading training tool and provide findings and insights from the design user study. Thank you.
Yeah, thank you, Professor Peng, for the great talk. And we have time for 1 or 2 questions. Any questions from the audience are welcome. Okay, so there are currently many paper reading tools that can make researchers' life easier. I wonder, how do you think about these paper reading tools? And how do you place a trainer for existing paper reading tools like ChatPDF?
The previous two speakers says they have developed the reading paper, the synergic. Yeah, I think these tools are great if our advisor asks us to summarize a set of paper and present this paper to them. That we definitely need these paper reading tools. But my point is the goal of the Crit Trainer is to help them develop the critical thinking skills, and I think this is necessary. And for every one of us, if you have time, we need to develop such kind of skills so that we can read papers independently without any support, and because we have such kind of skill. Yeah, I think skill is important.
Yeah, thank you, Professor Peng. And thank you. Let's give another round of applause to all the others.
Okay, thank you.
And our next speaker is Takumi Ito. Takumi Ito is a researcher at Tohoku University and the founder of Longsmith Inc., a startup focused on developing tools using natural language processing technology. And his paper is entitled Use of an AI-powered rewriting support software in context with other tools, a study of non-native English speakers. Maybe let's be patient. Same thing happens again. Shall we have the tech support from the back? Thank you.
So, hello, my name is Takumi Ito. I'm a researcher at Tohoku University in Japan, and I have also founded a company called Langsmith, where I have developed an AI-powered lighting support tools, the same name as the company. To be honest, I'm not good at English, so to assist myself, I'm developing the tools, and this work also investigates how non-native English speakers like me use AI-powered lighting support tools. So for researchers, it is very important to publish their research result in English papers, and it greatly impacts their careers. However, researchers with lower English skills like me face a variety of disadvantages. For example, writing a paper can take much more time. Moreover, even if they have a good research result, their paper may be rejected because of their English skills. So there are many tools to help non-native English speakers writing, one of which is a rewriting tool like WordTunes. The rewriting tools provide alternative texts to improve the quality. Most of them, rewriting tools generate multiple suggestions, so the users have to select the best one from the list. However, non-native English speaker, even selecting a suggestion may not be easy. So moreover, AI is not perfect, so it can make incorrect suggestions. So our research question is to understand how non-native English speakers evaluate the AI suggestions. Our team has developed a rewriting tool called Langsmith. In this study, we conducted a user survey using Langsmith as a research tool. This is a quick demo of the Langsmith. So when the user selects the sentence with their cursor, the Langsmith can provide several rewrite suggestions. This system presented in the ENLP conference. And Langsmith also provides a difficulty score for each suggestion. This score is calculated based on the probability given by the AI models. So a bigger burst means that AI think it's a better suggestions. And red indicates the deleted part, and blue means added part by the Langsmith. As a preliminary study, we conducted a user survey of Langsmith users. So we asked, what tools do you usually use when writing papers, and how is Langsmith usually used? We got a response from 39 Japanese people. Most of them are students or researchers because Langsmith is a tool designed for writing academic papers. As a survey result, 85% of the users said they use machine translation systems such as DeepL or Google Translate when writing papers. In addition, 33 of them paste the machine translation output to Langsmith for editing. Based on the survey result, we designed the main study to answer our questions. As stated previously, our research question is how do non-native English speakers evaluate AI suggestions? So we recruited 21 Japanese researchers and students by crowdsourcing. And we divided the participants into two groups, those who used the machine translation tools or those who did not. We collect data using two methods. First, we asked them to record their screen during writing. The writing task follows their IELTS and consists of the writing graph and table descriptions. Participants were allowed to use Langsmith and any other tools they liked. As a writing task, we also conducted interviews with 40 participants. In the main study, 50 participants used machine translation, and we found the two usages of the machine translation. First one is the forward translation. word translation means that input is a Japanese sentence and translate in English sentence. 6 participants drafted the full text in English, full text in Japanese and translate it into English. And 7 participants drafted some parts of the text in Japanese and translated the part into English. Another usage is a back translation. Back translation is translate in English text to the Japanese, and the back translation is used to check if the English translation is correct or not. 10 participants used the back translation approaches in this surveys. Back translation were also used for the text after they were edited with a longsmith. And longsmith suggestions are not always perfect. For example, sometimes words are dropped, so some participants did not notice their obvious errors when using longsmith, and then they found the errors when using back translation later. This suggests that they might not carefully check the suggestion before applying them. However, we believe that machine translation might not be sufficient to evaluate the quality of text. For example, machine translation can often translate a grammatically incorrect sentence, like I have a pen, correctly into Japanese sentence. So I believe machine translation is not good at to evaluate text qualities. Another way to evaluate suggestion is use difficulty scores. Based on interview results, everyone in MT group said they rely on the difficulty score to select the suggestions. Many of them also mentioned that they trusted the difficulty score due to lack of confidence in English levels, English proficiency. Furthermore, some participants say they only focused on the top suggestion and ignored the ones with the lower scores. And 6% of the members in the no-MT group, no-MT group means that not use the machine translation systems, also refer to the difficulty scores, but they did not rely on the scores as much as the MT group members. And interestingly, one participant felt that by following the difficulty scores, he gradually stopped checking carefully, resulting in the shallower elaboration. Our findings suggest that just providing machine-generated score is not sufficient for evaluating AI suggestions, especially for non-native English speakers. To help users evaluate the suggestion more confidently, it might be useful to show them the reason for the corrections and/or actual example used in the papers. We believe that development such user interface is an important future research directions. If you like, you can scan this QR code to use Longsmith. Thank you for listening.
Thank you, Takumi, for the amazing talk. Any questions from the audience are welcome. All right, I wonder, LLMs like ChatGPT can generate reasons for suggestions by dividing prompts. And do you think that would be enough to help non-native English speaker to make a choice here?
Yes, I think that ChatGPT is nice, and then the performance is very good, and then ChatGPT can generate some reason or some explanation for the suggestion, but the text, the explanation text also just generated the ChatGPT, so yeah, it has a product, and the non-native speaker have to check carefully the reason text. So,
yeah, thank you. And a question from the audience?
Again, Aaron Quigley. Natano ego wa jozu. Because you said at the beginning that your English language skill wasn't good, I think everyone listened to you more carefully and was paying attention to what you were saying more carefully because you said that. So expectation setting, both with digital tools and when you're speaking to other people, is very important. So have you thought of getting native speakers to look at the recommendations, not non-native speakers. Wakata?
Sorry, one more again?
Okay. You tested with non-native speakers.
Yes.
Have you thought of testing with native speakers, the suggestions?
Yes, yes, I think it is very good and very important, but my tools uses mainly non-native English speakers, so just in this study, just testing non-native Japanese speakers, only that.
But maybe pair a non-native speaker with a native speaker. The recommendations,
I see.
a native speaker will not pick the same as a non-native speaker.
I see, I see.
Maybe next time.
Maybe next year's WIST.
Yeah. Good luck. Thank you.
I will try later, yeah. Thank you.
All right, let's give another round of applause to our authors. Yeah. Our next speaker is Professor Xiang Anthony Chen from UCLA. Anthony's research employs human-centered design methods to build systems that catalyze advances in AI to augment human abilities. And his talk is entitled Marvista, Exploring the Design of a Human-AI Collaborative News Reading Tool. Let's welcome Professor Anthony. I may not be very stable, you just double click. Yeah. Yes, this part. It's there. Yeah.
Cool. Thank you for the introduction. I'm presenting Marvista, a human AI collaborative reading tool. So this is collaborative work with a bunch of NLP researchers from Salesforce. All right, so we know that 3 things are certain in life in 2023. So what are those? At least we can probably tell 2 of them, right? Death and taxes. So what's the 3rd thing that is certain? 2023 version.
GPT.
Yeah, generative AI is changing humanity. So that is something that is going to be very certain. For example, people have found that you can now use generative AI to help you argue your case in court or prepare legal documents as opposed to using human lawyers. But despite this kind of promises of AI, there's always a gap between what AI can do and what AI can serve humanity. And this has been a historical problem. So in this earlier work by Rick Caruana, they conducted a study in the mid-90s, and they found that doctors actually prefer, these lower performing rule-based models compared to the high-performing neural nets. So has anybody have any idea why this might be the case? Yeah, explanation, interpretability, because doctors want to be able to see how the model works and be able to change the model when they see any possible mistakes. So that's an example of this kind of a gap between the AI's performance and how it can practically serve humanity. So to close this gap, I believe by conducting human-centered design, we can achieve 3 levels of these human-centered objectives, so that AI can align with human values, assimilate human intents, and eventually augment human abilities. So if you want to learn more about these pyramid of human-centered AI objectives, I encourage you to scan the QR code and read another paper we wrote earlier this year talking about the next steps in this space. But today I want to focus on one of these objectives about augmenting human abilities. And in particular, I want to look at humans' ability to read long text, which I believe has been declining over the years, probably because of our overconsumption of short text, such as social media. So the question we're asking is, how might AI help humans process these kind of long texts throughout the reading process? So we can think about this question along the timeline of reading an article. So what happens before reading? And we found that before reading, it is important for the reader to decide what not to read. And historically, there has been some research about the distinction between receptive versus skim reading by Lanzer and Gardner. And people tend to read linearly, receptively by default, as indicated in this Nelson-Norman study, which shows on the right that if you don't do anything, people tend to just read from top to bottom of a web page, as indicated by the eye tracking visualization. There is little existing support to guide the reader how to skim the text strategically. So maybe AI can help in making these kind of decisions even before the reading starts. So explore some of these ideas. For example, to start, the user can think about how much time they want to spend reading this article. Let's say they set it up to 3 minutes. And then Mavista, this tool, will highlight a subset of text to help the reader stay within this time limit. And under the hood, we are utilizing some sort of extractive summarization model. We convert the user-specified reading time into a compression ratio, and then which serves as a parameter into the summarization model, and then we highlight the extracted text as the summary. Another thing we can do before reading is to think about how AI can help a reader filter this text by question. And this idea was inspired by Robinson's SQ3R reading technique that includes these processes of survey, questions, receptive, recital, and review. And this very important step of asking questions is kind of critical to help a user strategically decide how and which part of the text they want to focus on. So we use AI to generate a list of questions a user can answer by reading an article. And then the user can pick and choose which questions are most interesting to them. And then correspondingly, our tool would highlight a subset of these paragraphs. And the user can see which paragraphs might answer which questions they are interested in. So under the hood, we utilized question generation model. And know that this was implemented before the wave of ChatGPT. Of course, currently, you can use GPT for a range of these kind of features. But the high-level idea is that by enabling users to see what questions can be answered, they can plan their reading more strategically and more intentionally. So before reading, AI helps humans decide what text not to read. How about during the reading process? According to some earlier research, it's important to encourage readers to read reflectively. And reflective reading means involving interruptions by moments of reflective thought about the contents of the text, as opposed to going into the autopilot mode and just go through the text without much deep thoughts. So we ask, how can AI encourage engage readers in performing this kind of reflective reading? So in our tool, we first let the users go through the article one paragraph at a time. We provide some conventional active reading features like highlighting or taking notes. But also interestingly, we offer a third feature by which the user can ask AI to generate a question that quizzes their understanding of each paragraph. And by trying to answer this question, the user can realize whether they do understand the text they have just read. And if not, they can go back and revisit that paragraph. So during reading, AI helps humans reflect on the text they are reading or the text they have just read. So what happens after reading? By default, the user would see an AI-generated summary. This is just based on the text as is. However, according to Robinson's SQ3R technique, the review process is important. So we asked, instead of just reviewing the text as is, can AI help the reader review the reading process? And what does that mean? It means, can we incorporate some of these users' reading behavior into the generation of a summary? And it turns out there were several possibilities to achieve that. For example, the user can say, I want to consider how much time I spend on each paragraph. And then the AI would update the summary in a way that the user can hover and see, oh, well, this sentence corresponds to this paragraph, and this paragraph is included because I spend more time on this paragraph than the rest. And of course, you can argue that, well, maybe I want to flip this weight. I want to emphasize the paragraph the user omit rather than the user spend more time on, and that's entirely possible as part of the future work. And then likewise, you can treat notes or highlights as important considerations in generating this kind of human AI summary. So after reading, AI helps humans review both the text they read as well as the reading process. All right, to summarize, MaVista is a human AI collaborative reading tool that provides support, end-to-end support throughout the entire reading process. So with that, I want to conclude my talk. I'm happy to ask questions. And this QR code doesn't link you to this paper, but to another paper in which we talk about more ideas in the broader topics of human-centered generative AI. I'm happy to take any questions.
Question from audience?
Thank you for the great talk. One question that I have was regarding the quality of the text by itself. So knowing that let's say the generative AI or the system creating a question really depends on what context is being presented. So have you considered checking the performance on poor quality text, and how does it depend on that as well?
The question is, have we considered the quality of the AI-generated support?
No, the text itself, if the quality of the text itself is low, how it impacts the questions being generated by the AI?
The quality of the text the user is reading. We have not, but definitely this can be considered into the model itself. And you can, for example, update and improve the model so that the reader can ask AI to critique the contents they're reading. And that would be helpful for reviewing CHI papers.
Questions?
Hi, Kevin Poo from the University of Toronto. Great talk, and I really like how you ground all of these features from human theories and how people read and perceive things. I have a question on, I think most of the features are initiated by the human on, for example, I want to read for this amount of time, or I want to be interested in these questions. I wonder if there is a future, or I guess a potential to see that, even though despite our shorter attention span, we can nudge the user to, poke them with interesting questions or use these features as they are naturally reading the text to potentially expand our attention span again. Like, oh, did you know that, there's this interesting thing that was talked about in the next paragraph, and then direct the user to continue reading and continue to be engaged in the reading. I wonder if that would be an interesting sort of approach to another initiative.
Yeah, so can we use this tool to kind of expand the user's attention span? We haven't focused on this particular objective, but in our paper we discussed, actually our participants did spend more time compared to in the cases in which they didn't use this tool.
That's great, yeah. I guess there's some saving in us then.
Question?
Hi, I'm Carolyn from Northwestern. Great talk, and it's nice seeing you again. In the beginning, you mentioned how AI assistance and human agency are sometimes at odds, and we can kind of imagine like a much more extreme version of the tool where it just summarizes the whole article. So I was wondering kind of like, what is the decision-making process when you consider like what parts of this process, like reading, that we should maintain in the traditional way, and what parts are, I guess, allowed to be AI augmented?
Yeah, so which part of the reading should we kind of involve AI? So that's a good question. So we kind of overpopulate AI support because we intentionally want to explore this kind of human AI collaborative reading tool design. And our participants did realize the entire reading experience is very different. It took them some time of getting used to. So maybe in the future would perform some ablative study to see which kind of feature can be incrementally built into the existing reading environment.
Mm-hmm. Thank you.
Yeah.
All right. Thank you, Anthony and the team, for the amazing talk. And let's give another round of applause. Yeah, our final speaker is Professor Zhenhui Peng again from the Sun Tenzin University in China. And this time, his talk is entitled Storyfire, Exploring Vocabulary Learning Support with Text Generation Models. Let's welcome Professor Peng.
Hi, this is Zhenhui Peng again, and on behalf of my co-author, Dr. Xinbo Wang, Qiu Shihang, Jun Kai, Professor Xiaojuan Ma, and Professor Hua Mingqu, I present Storyfire, Exploring Vocabulary Learning Support with Text Generation Models. So, vocabulary is the basis for learning a foreign language, and to learn vocabulary, we need to first understand and memorize the meanings of target words, and then we need to master the usage of the learned words. So how do we normally learn vocabulary? Well, we can have the rote learning. We can try to remember a bunch of words using the dictionary, using the flashcard in a short term. But this approach may not a long-term vocabulary retention and practical word usage. We can also especially the existing HCI research try to facilitate vocabulary learning by using meaningful context like the video, like the online articles, and this actually they can help enhance the vocabulary memorizations. But they heavily rely on existing materials and seldom support other learning activities like productive and fluency development tasks like writing and speaking. So what if learners want a meaningful context for any target word set that users wish to run? We have the hypothesis that running vocabulary in batch under coherent context can help. But it could be hard for people to retrieve a context that covers any target word set. So also traditional teachers can provide in situ adaptive support like hints on word usage during the writing or speaking practice. But such support is often not available. Generative models can help. But how? Will AI assistants always be good in a running task? In this work, we design, develop, and evaluate an AI-generated story-based vocabulary running system, Storyfire, that can provide meaningful context and adaptive assistance for running any target word set. We adopt a two-phase design process to develop our Storyfire, working with teachers, runners, and HCI researchers. We first fine-tune a T5 model to generate stories given a target English word set. And then we evaluate and we verify with users that our model can generate meaningful context for any target word set. But what vocabulary learning activities can these models support? To answer these questions, we first interview 3 English teachers and develop the first prototype and test the prototype with the vocabulary runners and also conduct co-design workshops with English teachers and HCI researchers. And finally, we refine the Storyfire, and here is the user flow of Storyfire. First, the users can specify any target word sets by just adding the target word and the target words and check their meanings using a dictionary. And then they can click the Run with the Story button to check the generated story, which can help them to understand the target word's meaning. Okay, after this step is the story clone tag, is exercise tag. This exercise use the generated story as the material, and users need to fill in the blank using the target word. And this test aim to improve their to help them strengthen their memory of the target words. And the last activity is a co-writing activity. The users write the first sentence of a story using the target word, and the AI write the next sentence, and the users take the next turn to write the next sentence. And the AI also can provide some feedback on how many words the users write compared to how many words the machine write. Try to encourage people to write more words in this practice. In the user study, we want to explore how would the support from the generative model impact the user's vocabulary learning outcome and experience. And we adopt a 2x2 within subjects design with 28 university students. We compare 4 interfaces. The first 2 interfaces only have the read activity. They don't have the exercise. We have read send. They only can seek the dictionary and read AI interface. They can additionally read the generated story. And the later 2 interface, users can read the story and do the clone test and the co-writing exercise. The story sentence, the users in this story file send interface, users write the story without AI, and finally our story file AI interface have the full function of story file. So the procedure is on day 0, they did a pre-test to ensure all the run target words are unknown to the users, and on day 2 they run the words with story file, and on day 4 they conduct a post-test to check how many words they can remember and whether they can use these words correctly. The main results show that, of course, the additional clones test and writing practice can improve the learning gains. But we found that the Storyfile's AI features, it reduced the learning gains on the retention of target words meaning in the read, clones, write vocabulary learning sessions. It means that the AI assistance in the writing task is not helping. Why? Okay. Yeah. For the first finding, the clones test and writing practice, they increase the mental and physical demand of the task compared to the read-only activities. And participants with Storyfile AI spend significantly less time in the writing activities. Well, participants, they especially favor the adaptive writing assistant from Storyfile, but they perform worse. The generated stories are generally coherent and novel, interesting, but some of the stories were not coherent, which may be due to the lack of semantic connections among the target words. Our model may not be able to handle these conditions. Yeah. And the second consideration we run from these, our findings is that, the generated models is very promising to support the vocabulary learning activities by providing them with the adaptive learning materials. The most important part, we think, is we should balance the machine and human effort in the learning task. And future work, we should also handle the language ambiguity and generate diverse and harmless stories. And here I would also like to thank the reviewers. They raise very helpful suggestions. They suggest us we should identify the helpful characteristics of stories for vocabulary learning. It means what kind of activities are actually helpful for the learning task. Yeah. And in summary, we present Storyfile and AI generative story-based vocabulary learning systems, and we have insights for using the generative models for in the educational domains. Thank you.
Thank you, Zhenhui, for the meeting talk. Questions from the audience?
Hey, this is Chen from UC San Diego. So thank you so much for great work. And I was wondering, during user AI co-writing phases, have you guys thinking about the scenario when the user doesn't really like the AI inference results, and they might want to prompt the AI model to generate a new option for them, which might be more helpful for their writing? Thank you.
Okay, thank you. In fact, our model is not like ChatGPT. It does not enable the users to prompt the story based on their input. can just write the sentence, and the AI will generate the next sentence based on their previous written sentence. But that's a great suggestion. We explore the use of the ChatGPT. Of course, when we develop the Storyfy, there's no GPT, but we explored them later, and we actually found that GPT is able to generate a more coherent story compared to our model. But the thing is, we also found that GPT, the generated story is often more complex. Even we prompt it saying, okay, generate some simple story, no longer than 50 words, but the generated story is often more complex, and yeah, they may not be able to use by some the beginners of the beginners. Thank you.
Cool. Thank you.
Any other questions? I also wonder, like, how do you envision, like, your system could engage users to use in the long term? Do you have any plans?
Yeah. That's our next step, because actually, as we said here, we would like to use Storyfy in the wild with both learners and teachers. I think the gamification feature is needed for the long-term usage.
Awesome. Yeah, thank you, Zhenhui, and again for the amazing talk.
Okay, thank you.
Yeah. And finally, let's give a final round of applause to all our 6 amazing speakers and their collaborators for the amazing works at this session. And thank you everyone for coming to the amazing session, Right, Reading and Writing Tools. Please enjoy the coffee break and the rest of WIST 2023. Thank you.
All right, we're gonna begin in like a minute or so. So please, everyone, find a seat. All right, let's start. Okay, hi everyone. So welcome to the session, Creative Visions, Creativity Support Tools. My name is Andreas Fender. I am from ETH Zurich and Hanschikat. And yeah, so let's just start with the first presenter. So the first paper is going to be Beyond the Artifact, Power as a Lens for Creativity Support Tools, and it's going to be presented by Jingji Li. I'm sorry.
Thank you for the introduction. Okay, we can hear me if I stand by these mics. So if you take away one thing from these next 8 minutes, it's that when we see a creativity support tool, I also want us to be seeing a power relationship. And what do I mean by power relationships? Well, I think one place to start is through examining the verb empower, which HCI researchers love to use maybe a little loosely. So for instance, in this paper from 2005, the authors in the second sentence say, our goal is to develop improved software and user interfaces that empower users to not only be more productive, but more innovative. Even if we take a look at the UIST program today, there are several papers who have a goal of empowering end users in some way. So I would argue that when HCI researchers use the word empower, they mean it in this power to sense, the ability to do something. Technology helps mediate accomplishing new tasks, such as, how software drawing programs have the ability to undo strokes or organize your drawing into layers, which pen and paper don't. But I think there's another aspect of power, the power over aspect, which is the relationship between actors, that I feel like less work at UIST has focused on. And having power over someone isn't always bad. For instance, a tool designer could have power over the artists and users of their tools through focusing on certain features that they would build. But maybe these features could also be the same ones that give the artists power to accomplish something in the first place. On the flip side, artists may have power over tool designers when they demand a specific feature and they don't get it, and they're like, okay, I hate the ethics, so I'm going to cancel my subscription model to your tool instead. So to start to understand and question these power dynamics and to get a more precise definition of what we actually mean when we say the word empowerment in the context of creativity support tools, we conducted interviews with creative practitioners who were professional artists, tool designers, and CST researchers, often in overlap. Our end goal here was to build a theory of power, a generative theory, a la Wendy, Michelle, and Suzanne's paper, that could help explain existing power dynamics and give predictive, critical, and generative guidance for the future design of these kinds of tools. So we distilled these 6 themes that covered the concept of power and CSTs. You can read all of them in the paper, but I'm going to quickly, in the next few minutes, go through 4 of them today. What it means for artists to be empowered, the concept of what a normative ground is, and why artists need horizontal and vertical movement in tools. And before I dive into the ways they feel empowered by their tools, I just want to make it clear that creative practitioners are not a monolithic group. Some of them, particularly production artists who had full-time jobs responding to client work, felt empowered in ways that aligned with the current conversation at HCI. For instance, P1 said the most empowering experiences were those when they didn't have to think about the tool at all and they could just focus on the art and the tool would fade into the background, echoing ideas in ubiquitous computing. P3 said they felt empowered specifically by the Liquify tool because this was a great abstraction and great automation that let them edit entire parts of their drawing at once without manually changing each pixel in a way because it leveraged their existing skills of judging spatial relationships. And I think these 2 anecdotes align with what P8, a tool designer, said was their goal in building tools, which is, quote, to remove as many obstacles as possible, right, to enable a more efficient creative practice. But there are also artists who feel empowered not by making things more efficiently, but through the actual deliberate seeing and reflective process of creating art by making the invisible invisible. So some examples of this are P6, who felt empowered when art making intentionally structured their times towards focusing on specific objects and otherwise overlooked memories, such as the corner kitchen sink of their childhood home. Or P4, who made a typeface by erasing parts of celebrities' faces found in a facial recognition training set, said, quote, my art directs the gaze on the powerful rather than the marginalized. It's trying to authentically capture my kind of subjectivity and worldview. So for both these artists, empowerment meant having a creative practice that not only revealed something new to themselves about how they saw the world, but also their ability to share with others, right? They were empowered because they could exert power over their audiences to get them to view things in their perspective. So unlike interfaces from first wave HCI that were often designed to make office workers more productive at sort of these well-scoped tasks, I think it's hard to define and predict the bounds and requirements of a creative task. In fact, some creative tasks by nature may be defined by their misuse and appropriation of tools, such as the work of P5, who was a creative coder, who said, the interesting things are doing what tools are not designed for, citing that appropriation and remixing were core to their process and their pieces. So if we believe this, and if we believe that empowerment is not designed for through, pre-picking right constraints and levels of abstractions of our tools, what should we actually do from a technical level? Like, I think there is something to be done, which is that we can make tools that allow for vertical movement through different levels of abstraction and horizontal movement through other tools by building composable primitives, which also allow for interoperability and horizontal movement to other tools. So for instance, as an example, if we're doing lettering in Adobe Illustrator, right, a high level of abstraction here would be like just choosing a new font on your system. At a lower level, you could edit the kerning using the GUI in Illustrator, and maybe at the lowest level, you could convert that type to an outline and then actually just edit the individual paths on each individual letter. But if none of this works for you, for instance, you just don't like the font in the first place, what if you wanted to do it entirely by hand? Well, then maybe you can move horizontally to Photoshop, a different tool, a pixel-based tool, to then do that and do the pixel-based representation. I think these sorts of movements are really important to supporting the appropriation and adaptation to the unpredictable, emergent, messy, yet wonderful things we call creative workflows. So with new tools also comes new normative grounds. And what is a normative ground? Well, we are defining that as, quote, the way a tool structures its practitioners, ideas, goals, and intentions, shaping how someone thinks, acts, and expresses themselves. New normative ground means new considerations for power dynamics. For example, mental models and features, things that HCI researchers are very, aligned to thinking about, are parts of normative grounds. So Photoshop is a drawing, sketching-based mental model, while Illustrator is more of a vector-based one or like a shape-based one. But once you know that you can make Boolean operations, like how I made the mouth of the frog here in Illustrator, and once you have that mental model, you suddenly have more power than were you only to be sketching things, right? And while designers can't control every aspect of how a normative ground forms, a lot of it is sort of like the aesthetic norms and the cultural norms that then come around a tool, they can control the documentation of their tool, which is one way that normative ground is set because it's one way that artists first interact with their tool. In fact, I would argue that art making can also be a way to trouble these power dynamics by consciously standing against and even proposing new normative ground, as in the case with P5, who said, quote, the interesting stuff in art is peeling back the layers, which reveals to getting unique stylistic variations just following the docs won't. I'm always fighting the tools because they strip away all of the process by the nature of being coding-based. So I think this is where we stand in sort of the paradox of empowerment, right? The decision to make certain operations easier with a tool, the fact that tool creation makes things more accessible to more people, will then set a normative default aesthetic that then actually may result in uninteresting art to some creative practitioners. I think this is a way that tool designers exert power over their users, but also a chance for artists to create meaningful work like we saw with P5. So that's why allowing for vertical and horizontal movement may give creative practitioners a greater opportunity to appropriate tools in meaningful ways, hopefully mitigating uneven power dynamics between prescriptive tool builders and also artists. So at the end of this paper, I lay out an agenda for what I call artistic support tools, which is a way of conducting research that takes the power of artists and end users more seriously. So for instance, what if instead of treating CSTs as prototypes for effective design principles, we viewed them as probes to learn more about creative practices, or as a way for CSTs themselves to make normative claims? A lot of, I think, my past work in HCI has focused on championing artists as researchers, but now I would like to open the floor to the possibility that researchers can also be artists through their research work. So because it's only 8 minutes, I went through this presentation very fast, but if you want to know more, all these things are outlined in a zine of which I have about 20 physical copies of. So if you would like a copy of the zine, please come find me after the talk or later at the conference. And thank you, I'm happy to take questions now.
All right, if you have any questions, just walk up to the microphone and pose a question, please.
I loved your talk. Very, very nice. Great. I wanted to think about how artists work. And one of the things that we've found in interviewing artists and watching how they work and so on is that they are, by definition, creating their own methods, because that's part of the artistic process. And in doing that, they cannot simply take another tool that somebody else created and use it, because by definition, that's not the thing that they did. So they are tool creators as much
absolutely.
as tool users.
Mhm.
And in that process, then it seems like we have a very different view of what creativity support tools for artists is in terms of how we help them create their own tools.
Yes, like meta tools.
Exactly, meta tools. And so I really like the way you talked about horizontal and vertical, but how do you help them create their own tools, which I realize is a massively big question. So
Yeah,
try to-
it's a whole research agenda,
It's a
right?
whole
But a
research
very
agenda.
exciting one. I think one starting point is basically through, I think one thing that I see a lot in current systems is creating like end-to-end tools for artists. But if we were to focus on more like composable primitives that then artists could use to create their own tools, I think that's a great research direction. For instance, I know the like P5.fab paper that Nadia Peek's lab did, like they were like, oh, once we give the primitives of machine movement to artists instead of like a slicer that just converts to G-code of like a 3D model, then we see more interesting things because artists can then compose machine movement, which is like the fundamental base unit of the tool or like the task that they're trying to do.
Great. And I just want to say that I think this should be applied to a lot of other fields, because there's a tendency to say artists are these unusual, weird people who do things. But in fact, there's elements of this with all different kinds of users. Any kind of expert user has elements of this, and so we can learn from this and apply it more broadly. So
Thank you so much. Yeah, that's very sweet. And yeah, as I said, I think everything is about power. So I did this specifically for artists, but hopefully, yes, we can generalize. JD.
Awesome. Hey, JD Zamfrescu, UC Berkeley. Obviously, I adore this work. This is fantastic, and I love this framing. It seems like there's also even a broader question to be asked, not just about tool designers, but also about system capabilities exerting power on tool designers as well as the users of those tools. I wonder, I mean, this feels especially relevant now with all the sort of black box generative AI stuff where, you know, we're sort of in the thrall of what can they do? I'm curious if you have thoughts on those implications.
I do, yeah. I think that's a great point of system capabilities, right? I think one thing that came up in our interviews that I wrote a little bit about in the paper also is that like tool designers were choosing like, you know, what backend to use for their tool or how to build their tool sort of out of convenience. Like, oh, I use Paper.js because it has vector math and not because it's like related to anything about like the creative task that I support, right? So like a lot of tool designers are PhD students. They're like pressured to publish papers, be on that academic treadmill. They want to do things very efficiently. So I think like that also, like, right, that form of power. I'm not saying like tool designers are like monolithically like stomping on artists and stuff, but they also have constraints that they have to work within. Maybe this didn't exactly answer your question, but I'm happy to talk more after.
Thanks.
Thank you. David.
Hi, David Lindelbar, CMU. Super cool work. I'm probably going to poke a bit on the point that Wendy made. So how do you think your work generalizes beyond creativity support tools, right? Every time you build a virtual environment for yourself, being like, or even like really anytime you use a tool, you're repurposing, you're mispurposing. So how would I kind of, do you think, how would I apply your framework to, let's say, an operating system?
Yeah, great question. So how would we, like operating system for VR or just operating system
Just
in general,
operating system.
Yeah, okay, let me think a little bit. Well, I think it depends of like if you're a user of the operating system, right? Like one thing operating systems has is the constraint of like file systems. So then it's like, oh, now I have to think, and like the normative ground is in file systems, so I have to think of like, oh, where do I, like how do I want to organize my things into folders, et cetera, versus like if we look at the operating system of like mobile phones, that's app-based. So I think that's a different sort of way of thinking, and I think one way we can see this in like kids these days is apparently I learned that Zoomers are like most likely to fall for internet scams nowadays, and no one knows what an operating, like a file system is because they only use phones, right? So I think that's, okay, maybe I'm not exactly answering your question of like power, but yeah, I think like the point being is like the ways that the designers of these operating systems are making the decision and the ways that people have to interact with them are influencing larger components of their life more so than just sort of the direct task of like, oh, I want to like open this app or get this file system done. Yeah, if that makes sense.
Yeah, it makes a lot of sense. Also, I think the vertical versus horizontal framing is very important to think for us. But thank you so much.
Absolutely. Thank you. Thank you, everyone.
All right. Thank you so much, Shinji. All right, so the next talk is going to be X Creation, a graph-based cross-modal generative creativity support tool, and it's going to be presented by Xiang Anthony Chan.
All right, thank you for the introduction. I'm presenting this paper on behalf of the first author. And where's my cursor? So because as an advisor, unfortunately, I don't have all the important first-hand details, so I'll try my best to impersonate Zhang. All right, so this work is X Creation. Try to see. Okay. Oops. Okay, 1 second, sorry. Okay, I'll just go with this display. X Creation is a human AI collaborative design tool that focuses on using multiple modalities to facilitate a designer's creative process. So we know that currently AI support tools are increasingly popular, but in this trend, it's still important to incorporate human initiatives. And there has been a number of these previous work trying to bring human AI together, such as the duet draw on the right that allows AI and human to create drawings creatively together. However, most of these tools, they tend to just focus on a single modality, such as either images or text. So why is single modality not enough? Because other studies have found that it's actually quite important when humans think about creativity. They tend to be more creative when they are able to kind of traverse across more than a single modality. So we think it's important to bridge the gap between the current practices of just allowing creativity process on a single modality at a time. So we propose and develop X Creation, a tool that allows a story writer to start from one modality and then transition to another using a graph representation as kind of a intermediate representation to maintain the consistency and the controllability across modalities. So just to give you a very simple example to illustrate how this kind of workflow works in practice. So here you can see a designer starts with writing the first sentence of a story. And of course, we incorporate large language models to provide some auto-completion to make the sentence more creative, or just to auto-complete to save the user's effort. But another important thing that happens is that as the sentence is composed, it also is translated to a graph which extracts the entity and the relationship in between into this no-link representation. And the benefit of that is immediately you can see we can generate some illustration using clip arts corresponding to the entities in the graph. And the user can pick and choose which ones they want to move to the canvas to create a visual representation of the story they just wrote. And the user can proceed to either edit the text or edit the graph as the next step to continue the creative process. The user can even say, I want to create a node in the graph and offer a simple label, which then propagates to some text generation as well as a new element on the canvas. So let's watch a video that kind of puts some of these steps together. And it might appear to be a little fast in the video if it shows, but the high-level thing I want you to pay attention to is how the user writing a story is not just working in text or image. The user is able to freely move between different modalities, including the graph that connects the text and the images all together. And if you would like to see some of the in specific details in any of these steps, I encourage you to read the paper. There are figures that highlight what happens in each of those steps that is shown in the video. All right, so in terms of implementation, I just want to give you some high-level overview. There are 4 key pieces that makes this system work. One of them is the conventional approach of using language model to autocomplete the user's text that makes the story. And then 2 of the important pieces are the conversion between text and the graph. So when the user writes a sentence, it's translated to a graph. And when the user creates or edits a node, for example, in the graph, the text is updated accordingly. And then finally, we have a one-way translation from the graph to the image. Of course, it's tempting to think about maybe we can connect some image editing back to the graph and the text. But due to some of the technical limitation, we did not do that in this paper. We hope to maybe address that in future work. All right, so how does it work for the end users? So in our user study, we asked several of these research questions. So does our tool really enhance creativity? And is it really more controllable perceived by the user? And whether the graph as an intermediate representation actually plays an important role. And we compare our tool with 2 baselines, one being an existing commercial tool called AI Story Writer, and then also a vanilla text-to-image model. At the time of the implementation, we used the DALL-E tool. And our task at a high level consisted of 3 types of tasks. A closed-ended task in which the user replicated an existing story, like the 3 little pigs, and a semi-ended task in which the user rewrote the climax and the ending of a story, and then a completely open-ended task. So here's just an overview of the specific metrics we use to measure the user's responses to address the 3 research questions I mentioned earlier. So here I just want to quickly show some of the stories actually created by our participants. So in the first frame, you can see the user started with writing some sentence, which then populates the text into a graph. And then the user would drag and drop some of these nodes from the graph, which become some elements on the canvas. And then this kind of a multi-modal creative steps would happen continuously as the user unfolds the rest of the story. So without zooming into the detail in the interest of time, I just want to give you a high-level overview of what it's like to write a story in both text and visual modalities using our tool. And here's another example story written by our participants. You can see the incremental addition of more and more elements and richness as demonstrated in both the graph and the images on the canvas. And the high-level takeaway from our finding is that X creation excelled in most aspects corresponding to the 3 research questions. However, it also fell short in terms of faithfulness and efficiency, which I encourage you to learn more in our findings section in the paper. So in sum, we built X creation, a graph-based creativity support tool that uses AI to allow users to unfold their creative process across text, graph, and image modalities. If you have more questions, please scan the QR code. We have a Google Doc through which the other 2 authors can help you answer some of the questions.
Thank you. Are there any questions?
I'm going to start with one question. So I guess in the paper you're also a little bit right about this, but what I was wondering is when you have like inconsistencies in the input of the story writer, how is that represented in the graph? And basically what happens? Like, are those flagged by the system if there are like contradictory relationships between different entities? So what happens in this case?
So the question is, if there is any inconsistency, what happens? I think inconsistency is the precise reason we want to introduce the graph, so that the user would not be confused by some of the generated images being inconsistent with the text. So we did not observe any obvious inconsistent creation using our tool.
Yeah, okay, great. So, Ihao Carnegie Mellon, really great talk. I want to ask a little bit like lower detail or low level question. So, in your pipeline, there's like this traditional NLP pipeline where you use like some entity like extractions. Yeah. There's like to kind of create this like triplet representation from subject, relation, objects. I wonder, have you tried, like the team tried the using like GPT, like the large language model as a whole for kind of replacing some of the traditional pipeline? If that will work, then maybe some of the components in the system could be more unified. I just have that question down.
So we did use GPT just for the text modalities alone, and we use SPACY, which is an NLP library. It's very basic. We didn't feel we need large language models, but maybe it's something we could try in the future.
Okay.
We have time for one more brief question.
Okay. Hi, thank you for the paper. Eric Ron, UC Berkeley. I'm wondering if there are any like concrete behaviors that we're expecting the tool to change, right? Like in addition to maybe asking people about their perceptions about the use of the tool, like it seems like what you're going for with the project is about changing creative process, and I'm wondering how that would show up in like how people's behavior with the tool actually changes and how we might see that. If there's any kind of specific kind of like concrete things that we can look for in people's usage.
Yeah, the question is if we observe any changes of behavior. So the most obvious behavior is that people no longer just write text or draw images. As you see in the video, initially they might feel this is a little overwhelming, as we observe in the study, but as you can see in the users, the creative stories, gradually they became more and more used to, I can write and then I can play with the graphical elements and then I can translate them into the visual modalities. So they become used to this new style of cross-model creation process. That's the major change as opposed to single model creation. All right.
All right,
thank you
so much.
If you have more questions, I will relay those to the first author. I'm sure she can answer them much better.
All right, thank you so much. Okay, so the next presenter is setting up. So the next paper is going to be Interactive Flexible Style Transfer for Vector Graphics, and it's going to be presented by Jeremy Warner.
Sweet, thank you for the introduction. So my name is Jeremy Warner. I'm a recent PhD graduate from UC Berkeley, and today I'll be telling you about style transfer for vector graphics. So vector graphics are the de facto format that designers generally use for graphic design. Entire ecosystems of commercial tools have grown around creating and editing these graphics. Designers often take inspiration from other designs, manually mixing and matching visual styles. These examples can serve as a vocabulary to explore new visual themes and ideas. Meanwhile, style transfer has shown impressive results in raster images, and so we want to explore whether this is possible also for vector graphics. Vector graphics contain graphic primitives with higher level attributes than raster images, so a circle's radius, text font family, or fill color, for example. And while this lets designs be edited at a higher level and scale to various sizes, we can't use image-based style transfer techniques directly, as we want to retain the output as a vector graphics design. And so this work operates in a space where optimality is not necessarily clear. What does the best style transfer output generally look like? We want a sweet spot in creative control past manual work and requiring designers to do everything, but short of a fully automated process where we can still support designers in having some creative control. So I'll be presenting VST, our tool for interactive, flexible style transfer for vector graphics. Given a source style and target structure, so two separate designs, VST provides a way to load and flexibly transfer visual styles across these designs. This results in a new stylized vector graphics design that can be exported and used anywhere else. And here are some results of transferring visual styles across vector graphics, all done using VST. So there's some more results in the paper, and I had other examples online, but I just wanted to showcase some of the possibility here. And due to some of this inherent subjectivity around what good style transfer is or looks like, we aim to support designers' creative control by exposing how the transfer actually takes place and giving a lot of control over that process. So our three design goals were to, one, enable high-level tuning of cross-design element correspondences, enable flexible control over which style attributes are transferred, and reduce the work and time required for transferring design styles. The core enabling mechanism for this style transfer is a technique for generating a correspondence or connection across two sets of design elements. So rather than using something more opaque like a diffusion model, we instead infer classes of similar elements across designs and then facilitate propagating attributes like color, fill, font, or size. I also won't discuss the full details of constructing this correspondence in this talk, but there's some additional details on how this correspondence between designs is learned in prior work. The styling interface consists of four main components. So first, there's the source design canvas, the target structure or content design, the stylized output target, and the styling or matching pane. Initially, once these designs are loaded, applying source styles to the target is as simple as pressing copy all. However, this generally uses the default inferred correspondence, which may need to be refined, or how the styles are applied might also want to be customized. So designers can select a desired target to change, a desired source style to match, and then propagate or transfer that to other similar elements in the design directly. So essentially choosing an example to replicate in their design. Designers may also dynamically adjust their output selections to other similar elements. So essentially, if you have similar elements or patterns, groups of objects you want to style in the same way, you can flexibly extend the selection. Designers can also, given the selections and elements that they've linked, designers can also adjust which attributes from the matched design that they actually wish to transfer either globally or for the current selection. Okay, so that's kind of the overview of how it works and what VST's features are. In evaluating VST, we focused on three research questions to learn how VST can support designers. One, how would experienced designers use VST to stylize basic designs? Can VST adapt to styling more realistic or open-ended designs? And can this actually reduce the time or work required needed for some of these style transfer tasks? To do this, we ran 2 user studies exploring designers' responses to VST and the VST's comparative ability for transferring styles. The first involved transferring styles across designs that let the that the designers brought in before the study based on a given text prompt that we provided them. And generally, given these two designs, participants were asked to make the target design or output design in VST as visually similar to the source style as best they could, kind of in their own interpretation. And so kind of a snippet from this is that while many of the transfer results were homogeneous, especially in the more simple designs, more complex designs yielded higher variance in the end output, kind of suggesting that there is some autonomy or creative control that designers can use VST to express. Also, participants use the interface to create consistent visual styles on a range of target designs that match their created source design. So in this case, participants created this top row of designs beforehand, and then use VST to generate this inner table of designs by modifying the target design that we provided them and stylizing it. So vertical columns show a single consistent design per participant, and horizontal rows reflect the structure and content of the template that we provided them. Okay, so we also did a follow-up evaluation that was exploring the kind of efficiency in actually editing this. So we did a recreation study where 4 expert designers use a traditional vector graphics editing tool to essentially match and recreate the VST output from the original study. The source design was provided as vector graphics, and the the goal was provided as a raster image to try to recreate. And also they started from 2 conditions because we wanted to acknowledge that there's some advantage that VST provides by automatically styling it. So in addition to the basic, just giving the raw template, we also allowed them to edit, or we also asked them to edit from the kind of default stylized VST match and manually match the style in both cases. We find that VST can significantly reduce require less time and work than experienced designers using industry standard tools. So this is the duration, amount of edits and selections per this recreation task. And interestingly, the auto baseline, which you might expect to be easier if it's VST's default output and then editing that towards the end goal, that was actually somewhat slower and required more edits, at least in our study, when you'd kind of expect the opposite. The algorithm should progress towards the goal. So the idea here is that a partially correct transformation can actually reduce the cohesion for future editing. And while ultimately not significant, this suggests how the current landscape of design tools aren't maybe quite prepared to take advantage of more advanced mechanisms for editing designs, while allowing for the designer to still retain control over the final output. And so to summarize, VST enables some faster and easier vector style transfer, and 2 key features that were essential to find this algorithmic sweet spot were essentially tuning the generated design correspondences and how designs related to each other, and also tuning what it meant for the designs to be connected or correspond across designs. Okay, so thank you to my wonderful co-authors, Frederick Kim and Bjorn Hartmann. This work would not have been helpful or possible without. And there's some more details in our paper at this link. We also have a demo up with some example graphics. And yeah, so that's my time. Happy to take some questions. Thank you.
Thank you, Jeremy. Are there any questions? Okay, I can start with a question. So could you also think of sort of other use cases which are maybe also incorporating dynamic elements like game UIs or something like that, where you also have vector graphics, but in a different way, so to say, right? So did you think about that in any way?
Yeah, that's a great question. I think a similar technique could be useful in other kind of domains like 3D assets or games where you have kind of a mix of media. I think the selection mechanisms or how you edit and transfer might be different, but a lot of the same concepts will apply in terms of wanting to basically, maybe there's not an optimal automatic solution where you just run your algorithm and it generates the result exactly, but I think there's a better way to do it than forcing people to manually edit everything directly.
Yeah. Right, thank you.
Well, that's really bright.
Hi, Yuan Liu from University of Notre Dame. Really cool work. I have a question regarding the last part you were discussing, like full automation might even increase the time people work on these stuffs. What are some of the hunches or explanations you come up with that process? My hunch is if I have an expectation of how the outcome is going to be and the automation process gave me a different result, it actually takes me more time to do it to fit into like what I really want to achieve. Do you think that's something you saw in your experiments, or?
Yeah, so I think my explanation or kind of hunch here is that if you only provide an automatic approach without also providing means to tailor how that automation is directed or explore alternatives, it can actually basically increase the amount of work to adjust towards the final goal. Whereas in theory, you think like, oh yeah, it's just progressing towards it, but there's often people will want very different things, right? There's not always a clear immediate case that like, oh yes, this is the result I want. I should just automatically apply an algorithm and then it's perfect. So,
cool, thanks.
Yep, thank you for the question.
There's time for one very brief question.
Hello, Michael Schnebley from Harvard University. And my question's also about alternative applications. It strikes me that in audio synthesis, there's an analogous situation at hand, where on the one hand, one could be working with raw waveforms, which would be like the raster form of an image, and on the other hand, one can be working with higher level parameters that determine what the audio waveform is, ultimately. And I don't know where, what the frontier of generative audio is right now and where the tools that exist currently lie in that space, but I'm just wondering if you do, or if y'all have, or if you have any inkling of or have been thinking about audio synthesis with regards to this tool.
I like playing music. I haven't directly basically done research in audio synthesis, but I think the idea of style transfer for other domains like audio is super interesting, right? Because I think there's an inherent ambiguity in terms of what it means to transfer the style across rich mediums like this that aren't inherently just, a set of colors or something. There's a lot of attributes and properties of music or a design that you might want to consider, and what it means to transfer the style could vary wildly both on the two sources of music that you're considering and the individual artist that's kind of creating or facilitating that transfer process. So I think some of the things here that might transfer are trying to instill a sense of creative control in terms of that process while, not, I guess for music, I'd be curious to see what the actual kind of means of doing that are like, right? What does it mean to like select, is it the tempo? Is it like the, how do you just grow the feel? I feel like music is, almost nefariously like hard to describe, and there's a lot of adjectives and subjectivity. So, but with that said, I think it makes it even more interesting to explore how people would actually do that.
Yeah. Thank you.
Yeah, thanks for the question.
All right, let's thank our speaker. So the next presentation is going to be Curve Crafter, a system for animated curve manipulation, and it's going to be presented by Nora Willett.
Okay, thank you. So I'm going to present Curve Crafter. So line work on 3D animated characters is an important aspect for stylized looks for films. And while there are multiple ways of stylizing and creating lines for these looks, it is very challenging to add, edit, or delete automatically created animated silhouette lines. So silhouette lines are the black lines shown here, which lie on the edges of a 3D mesh that separate the visible parts from the invisible parts. So to solve this challenge, we propose a novel UI, Curve Crafter, which allows users to draw, edit, and erase new lines on 3D models. And these lines are deformed with the model and interpolated between frames. For silhouette lines on characters, users can deform or erase the lines on one frame, and the changes will be propagated to nearby frames. Our workflow improves the experience and reduces the tedium of manually editing every frame to fix discrepancies in automatically generated silhouette lines. Our contributions are a UI with tools allowing users to edit the shape and opacity of 3D silhouette curves, an algorithm to propagate edits on silhouette curves between frames, improving temporal consistency, an evaluation with 5 professional animators using our system to create line edits on 3 shots, and comparison of our system to Disney's animation's Meander using a shot from the short film Pete. Our UI, which has not yet been used in production, is developed inside of Pixar's animation system called Presto. It leverages the existing 3D viewer and pose editor. So next, I'll discuss the different UI tools available in the system. The Draw tool allows animators to create curves which are projected onto the model. By right-clicking, the user can select a curve to redraw its shape, and these curves can have parts on and off the model. Curves then deform along with the model between frames. Using the Edit tool, users can scale, rotate, translate, or deform a curve. Then the system interpolates between the curve shapes. Users can also erase curves. And to see and edit the timing of a curve's keyframes, the user can select a curve and then delete it, move, or add keyframes in the pose sheet at the bottom. So in addition to drawn curves, our system also generates silhouettes for a character and viewpoint. Similarly, the Edit tool can be used to change the shape of the silhouettes. And these edits are propagated across curves on subsequent frames. With automatically generated curves, an additional tool allows artists to revert an edit by brushing over the shape. And the Eraser tool can be used to change the opacity of curves. With the Reveal tool, erased portions of curves are highlighted, and then the user can brush over them to turn them visible again. So with these tools, users can add to and edit automatically generated silhouette curves for creating additional character personality. Our automatically generated silhouette curves are represented as 3D polylines and are extracted from the surface mesh by tracing the zero level set of the dot product between normals at mesh vertices and the view direction. While visible curves are calculated at each frame, we create correspondences between different frames by vecting curves from the previous frame based on the mesh movement between frames. So these track correspondences allow us to propagate edits between frames. If we only propagate edits between frames and do not interpolate those edits, then as a curve expands and add points, newly created points in the middle and end will not have any offset information, causing temporal inconsistencies. For example, with one keyframe, just copying the edits creates a new curve that is broken up. In our method, we topologically interpolate along the curve to determine any missing offsets. If there are multiple keyframes, we first topologically interpolate each keyframe's offsets and then temporally interpolate between them. We use a similar method to propagate opacity between frames. With our interpolation algorithm, we can produce smooth silhouette edits as seen on the left. Please see the paper for more details about our algorithm implementation. So next, we asked 5 professional animators to use our system to add lines to 3 different shots. So here, the animator changes the silhouette lines around the character's arm. Notice how they pulled the arm shape out to exaggerate it. So this animator added lots of details around the face and eyes while adding bubbles as the character flies away. In this instance, the animator decided to clean up the silhouette lines around the character's eyes. They erased the silhouette lines and redrew them. They also added bubbles at the end of the animation. Here, the animator edited the shape of the silhouette to make it drag behind and break off to form a bubble. This animator edited the silhouette extensively to overemphasize the reaching out and back of the character's arms. They edited the shape of some of the silhouette lines, while for others, they erased and redrew them. When asked how this tool could be used in animators' workflows, they mentioned 2 main areas. One was the ability to quickly add face details to push the expressions and appeal of the character. Another was being able to draw effects or folds in the cloth, which could then be passed to simulation department for guidance. The animators also had several suggestions for improvements to the toolset. Users wanted a more streamlined selection for the curves. So currently, each tool requires a curve to be selected. The Redraw, Edit, and Retiming tool all has this. And then it has its own selection inside the tool before the operation can take place. With a single persistent selection tool, subsequent actions would know which curve to act on. All animators also suggested the addition of a smoothing tool, and this option could be used to brush over drawn or edited curves to remove small bumps or jaggies. When using the erasing tool, animators requested that the erased user-generated curves behave more like erased silhouette curves so that the reveal tool can work on both types. This change will allow animators to erase parts or all of a curve at a frame and then make the exact curve reappear later on. Animators also wanted to control the size and the strength of all the brushes. We also wanted to see how our system could improve the workflow on the short film Pete. The FX lead used our system to recreate some edits, which were previously done in Meander on this shot. The Meander system is a hybrid of a 2D animation system with 3D input. Artist-drawn curves from a starting frame are advected to subsequent frames using a vector field calculated from the motion of underlying 3D models. To make changes, each frame needs to be investigated and individual curves edited. Our system resulted in 43% fewer keyframes than when using Meander. Some fixes included erasing an ear line, erasing armpit lines, erasing and redrawing a part of the hat, and erasing and redrawing the chin gap. With our system, the FX lead was able to add lines to close gaps, which they were not able to previously do in Meander due to trouble matching the pen pressure and style over multiple frames. In summary, our system allows animators to edit automatically generated silhouette curves while ensuring temporal consistency of those edits between frames. Thank you.
All right, any questions? Yep.
Hi, Jasper Tran-O'Leary from the University of Washington. This is super cool. I actually didn't know about silhouette curves at all and kind of like the trouble that they posed. I was curious, you mentioned that kind of from the user study, animators wanted to do extra detail to like the face and kind of like the effects like the bubbles. Do you see these as like areas for future development of the system or different tools altogether?
I think this system could eventually lead to that. The challenges would be mainly getting departments to talk to each other and put it in actually the pipeline of production in some format that can be passed down to departments and everyone agrees on the right setup.
Gotcha. Thanks.
Hi, Nora. Great talk. I kind of have a similar question to Jasper's. Specifically with some of the changes you saw to the character or augmentations to character pose or facial expression, do you see an opportunity for a pipeline or did animators express an interest in modifying 3D character animation based on the perimeter sketches they were creating with your tool?
Yeah, so the animators did want to do that. There's actually already another tool in Presto that does do that. Where they can draw the silhouette and it will deform the model to that silhouette. So this does a slightly different, but yes, animators wanted that and I informed them that there was already a tool that does that.
Cool, thanks.
Hi, Brandel Zacharnik, Apple. I'm really curious, you mentioned that there are 3D polylines under the hood, but it looked like the editing was done in a monoscopic screen space. Would this be able to extend or with additional sort of angles of capture into arbitrary camera angles in a monoscopic 3D or into a stereoscopic context for being able to reproduce these polylines?
So the polylines are all in 3D and then the user draws on them in 2D with it being projected back into 3D. So if you're doing, and you can change the viewport to draw the lines in different angles. So editing can happen by changing the camera around, and then since they're in 3D, then they can just be rendered out from stereo or single camera.
Hello, I'm Takebura from University of Tokyo. So my question is it possible to apply this method to silhouette rendering of fluid simulation or something?
Could you repeat that? Sorry.
Fluid simulation, water splash, and so on. Can you apply this to water splash and, water simulation, something?
So the tracking of the silhouette lines requires that the mesh be consistent. So we have had trouble with, if you have a simulated mesh, then the topology of the mesh is not consistent over frames, so you can't track the lines, which this relies on that tracking to propagate the edits. But you could use this to draw on the mesh on individual frames, but then the lines wouldn't be able to deform over time either because you need a consistent mesh underneath.
So currently not supported.
So currently,
but
not
maybe.
supported. You need some way to correlate the
Interesting.
simulation
Thank you.
meshes.
Good. Yeah.
All right, thank you, Nora.
Yeah.
Okay, so the next paper we're going to hear about is P-Colorizer, Recoloring Ancient Chinese Paintings with Ideal Congruent Poems. And it's going to be presented by, sorry, the name here was, you're not the first author, right? Second. What's the name again? Jung Hang Wu, sorry.
Hello everyone, I'm Mian Hong from Zhejiang University. Today I will introduce the latest work of our lab, namely P-Colorizer, recoloring ancient Chinese painting with ideal congruent points. Ancient Chinese paintings are both witness of Chinese history and the inheritance of Chinese culture. However, most of them have suffered from varied degree of color fading problems. To extend the life of these color fading paintings, the traditional methods relies on the manual restoration of professional painters. Especially, they must inverse the original color with faithful reference first, and then perform chair and air colorization to achieve satisfactory results. This process is challenging and time-consuming, typically spending months to years for a single painting. To improve the efficiency of color restoration, we employed image-to-image matching techniques in the early stage to quickly search for the reference paintings. However, due to the color fading problem, we found that the search results contain few paintings with accurate color schemes. With the deep understanding of the domain, we discovered a new medium, the point inscribed on the painting. As one of the most renowned painters, and the poets Sushi said, both painting and point are artist forms for literary to borrow scenery to express emotions. A specific manifestation of this principle is that painting and points often contain the same object to convey congruent conceptual feelings. In Chinese culture, these objects and conceptual feelings are called imagery and ideal. Compared to the visual paintings, the textual points have been better preserved, serving as essential mediums for identifying references. However, two challenges still exist when applying this principle. First, ancient Chinese points are high-level abstract words that are difficult for cross-modal alignment. Second, it's not easy to find correct color schemes in large-scale reference paintings. To overcome these two challenges, we collaborated with two restorers who have more than 10 years of experience in restoring ancient Chinese paintings. Based on their interviews, we summarized a list of user requirements and proposed a novel interface system called P-Colorizer. For color fading paintings, P-Colorizer uses a point congruence module to search for reference paintings, design visualizations to help color scheme analysis, and employs a user-guided colorization module to support fast colorization. The interface of pixelarizer contains three fields, namely border field, timeline field, and the reference field. The border field comprises a painting board and two collapsible panels at the right and bottom. Users can construct the search query and modify the characterization results here. The timeline field is comprised of mountain mandibles and a hierarchical bar chart. The mountain mandibles visualize the congruence scores and the temporal distribution of paintings' color schemes. User can expand the mountain mandible into a glyph-based scatter plot to explore the similarity between different reference paintings. The hierarchical bar chart summarizes the color space extracted from the reference paintings. User can use the hierarchical bar chart to control the color scheme displayed in the mountain mandibles. The reference field introduces heat maps and a preview window to illustrate the model insight about the concurrence principle. In the heat map, the red covers the region with high concurrence, while blue covers the region with low concurrence. To prove the effectiveness of the concurrence principle, we compared the color histogram of reference paintings searched based on the color fade paintings and its idle concurrent point. We found that the reference paintings searched based on the point involve more bright colors, which means that the concurrence module appears to understand the idle. Moreover, we also explored how the point paint concurrence module understands two other idle. Finally, we play a specific case to show how a restorer utilizes pixelarizer to restore a color fading paintings.
I first browsed the entire painting to understand the fading of different imageries. Then, he used the lasso tool and the grid-based text component to construct a query of reference painting search. After clicking on the search button, he noticed the Ming Dynasty had the largest number of reference paintings, which also showed high congruence scores. Hence, he decided to view the paintings of this dynasty first and clicked on the corresponding button. In the glyph-based scatterplot, he found two painting clusters had different color schemes. He clicked on the glyph of painting A and then viewed its color scheme in the hierarchical bar chart. For the color scheme, he used the selection function of the hierarchical bar chart to control which colors will be displayed in the mountain metaphors. After a period of exploration, he found that only one blue color has not appeared in the dynasty where the color-faded painting was created. Therefore, he added painting A to the reference list. After confirming the correctness of the ideogram understood by the point painting congruence module, he utilized fast colorization tools to colorize the faded imageries. After uploading,
thanks for your listening. I'm happy to take any questions.
Hi, Chisun from UC San Diego. I noticed that you will restoration the painting and the poem, but to my knowledge, only a few paintings have a corresponding poem. But my question is, what's the next step, or what you can do when you only have the color faded paintings to finish the restoration?
Thanks for your questions. I agree that not all ancient Chinese paintings has its idle concurrent points, but in fact, most of the surviving ancient paintings have textual record in formats more than points, such as the comments left by their collectors. Considering that these collectors has a closer temporal distance than us to the original paintings, So I think their left comments are the valuable cues for us to find the reference paintings. So given the powerful capabilities of the cross-model alignment models to learn various text formats, I think the Picard Writer can handle this case if you can fine-tuning the model or take more some feature work. Thanks.
Okay, thank you.
Hi, this is Rui Shi from Tongji University, and I'm very impressed by this work, but I have a little bit of technical detail that I want to ask. So I know that Chinese poems, they are pretty much very abstract, and so how do you in this system try to match this sort of contextual information to the let's say the painting itself?
Yeah, the Chinese point actually abstract words, but in our work we take it as normal text to Chinese date. I convert the model, the performance of the model may be influenced by the abstract words, but our system are flexible for the more powerful closed model. So the model is not our first contribution. The first contribution maybe is the system to support the color restoration work.
Okay, thank you.
Hi, this is Ren Lin from Purdue University. Okay. So very nice work. So I just have one question. Like from my knowledge, maybe wrong. Like there are a lot of Chinese paintings are actually in history. They are created in black and white color. They are not like like Western art. Like they have many color. They are focused a lot on the color. So how do you deal with this? Like are there a lot of examples of colorful Chinese paintings that you can use to build up your model, or
for the data set, our lab has made much effort to build such a data set. We take the image data of the painting from the internet, or take it offline in the museum. So the reason why we not open the data set, maybe some paintings was not available on the internet. So actually we have collected more than 20,000 paintings data. So this data as the basis for the Chinese our models.
Thank you.
Thanks.
All right, thank you, Yanho. Okay, so the final paper of this session is a Tailstream, Supporting Story Ideation with Trope Knowledge, and it's going to be presented by John Peck-Shu.
All right, great to be here. Hello, can you hear me well? Is it working? Oh, great. Yeah, so my name is Jean-Pec, and today I'll be presenting our work on supporting story ideation with trope knowledge on behalf of my collaborators and mentors from Adobe, Stanford, and Roblox. So as many of you might already know or can imagine, creating stories is a demanding and artful process. Transforming a nascent idea into a fully developed story comes with a lot of challenges, from developing intricate characters to structuring a plot, delving deep into themes, or crafting nuanced sentences. In attempting to support story creation, many systems ambitiously aim to tackle all these issues at once with holistic approaches. Recently, text generation systems with various controls or visualizations have especially grown popular, as we've notably seen yesterday or today earlier. Papers assessing the potential of LLMs for supporting story creation have especially pointed out the suggestive power of these tools. While the specific words generated by these models are often completely revised, the underlying ideas sparked by these words have reported to be particularly stimulating. Authors find value in iterating over ideas to craft their unique narratives. So in our work, rather than holistically tackling story creation, we proposed a focused approach on supporting story ideation, meaning the initial stage in the story development process where ideas for stories are conceived, developed, and organized. This phase is crucial as it sets the foundation for all elements of the story later. But how do people find ideas and inspiration? Well, to ideate stories, authors often draw inspiration from other works and lean on common narrative elements such as the popular hero's journey structure, or the diabolical mastermind character, or maybe the complex dynamics of a love triangle. Narrative theorists like Vladimir Propp and Roland Barthes, among others, have argued that essentially every story can be distilled into a handful of core narratives, even Twilight here. These storytelling devices or narrative patterns can commonly be referred to as tropes. Tropes offer a familiar and popular taxonomy of narrative elements. They have been thoroughly annotated for nearly 20 years on the WikiLive website tvtropes.org and now form a rather comprehensive storytelling vocabulary of more than 27,000 elements collected on the website. So on this wiki, you can find definitions for tropes, like here for the diabolical mastermind, but also some semantic categorization. So diabolical mastermind is part of these categories here. And you also have presence in different movies, and also additional links between tropes that organize this knowledge. So focusing on story ideation and tropes, our work introduces Tailstream, a canvas system that leverages tropes as story building blocks to suggest story ideas. To suggest ideas to the user, our system can output lists of trope instead of generating continuing text or auto-completion. Tropes here allow to rapidly browse many ideas that are part of a shared storytelling vocabulary. For instance, based on the word alien here, our system retrieves related tropes that can fuel the user's imagination, such as the tropes starfish alien or alien among us, which we can add to our canvas. Tailstream provides controls over these suggestions by letting users select the inputs, which can be both text and tropes. For instance, here, the combination of the trope starfish aliens and the text input love results in trope suggestions at the intersection of these themes, such as humanity is infectious or interspecies romance, that we can again add to our canvas. We additionally provide controls over the suggestion type, privileging either exploitation or exploration through our breadth slider. A lower breadth results in semantically closed suggestions, whereas a bigger breadth proposes broader suggestions based on co-occurrences in movies. We also propose to use filters to specify the intents and navigate the story knowledge space. By filtering on the settings category, for instance, we only have setting suggestions, such as these ones here. Similarly, by filtering on specific movies like Avatar, we're only suggested narrative elements present in the movie Avatar according to and thanks to tvtropes.org database. Finally, we provide more details about tropes extracted again from the wiki. These include definitions of each trope or how they're used in various movies as application example for more inspiration. Now behind the scenes, first all the data again is used by our system was created from tvtropes.org. One of the main components of our system is our trope suggestion tool, which recommends tropes as story ideas based on both text and tropes. To satisfy this goal, we propose two algorithms. We leverage the categorization proposed by tvtropes.org as well as trope co-occurrences in movies. In essence, our algorithms rely on a TF-IDF algorithm by considering tropes as documents and categories or movies as words. In our user study with 96 participants, we evaluated these methods, here called index and co-occurrence, against a random algorithm for baseline. Each of them was asked to describe some outputs from the algorithms, as shown here, and rate their satisfaction with them if they were to create a story. In a nutshell, based on these result scores, the suggestions of our algorithms showed different qualities and were preferred to the random baseline. After piecing together the different components, we also evaluated the whole system with 10 users, including 5 professional story writers and 5 hobbyists whose backgrounds include filmmaking, literature, improv, and more. Each participant was given 20 minutes to imagine a story from scratch using our system and was then interviewed. The reactions from our participants were overall very positive, with many of them sharing their excitement. Users notably pointed the system's effectiveness to tackle writer's block. Answers to our questionnaire notably show support for both convergent and divergent thinking. Users overall found the suggestion very helpful and the controllability efficient to browse the options. The use of tropes as frameworks specifically all along this process was found beneficial for many reasons, including structuring stories, having a mental image of an idea, or gathering knowledge by finding common practices and actual examples, for instance. Among the future directions opened by this work, many participants expressed their desire for complementary outputs to the use of tropes. Text, whether retrieved or generated by LLMs, for instance, can provide more specific details, while images or videos can help better ground ideas. Finally, even though all the participants ended up being satisfied and confident in building their stories, a few participants reported that over-reliance on tropes is a trap the system should point out and be careful with, which we seriously take into account and discuss longer in the paper. So feel free to check out our paper for more details, and thanks a lot for listening.
All right, any questions?
Hello, Jasper Chan-O'Leary from the University of Washington. This is a super cool tool, and I could definitely see myself using this when trying to think of new story ideas. One question that came to mind is that I guess sometimes tropes are bad. I can give examples, but you wouldn't necessarily want to follow that trope or use it in a story at all. And I was curious how the system currently thinks about that, or how you might do so in future work.
So thanks a lot for these questions. I'd say right now the system currently doesn't support any feature for this specific question, but generally it depends on what you call bad. All tropes have perks and disadvantages. If you think of each trope in the most straightforward way, yes, it might be dangerous for creativity and spread stereotypical harmful representations. But I'd say all stories are based on tropes and all kind of tropes. And the best stories succeed in integrating tropes artfully to find the right balance between comfort for both the writer and the viewers, for instance, between comfort and surprise. So I think just storytelling masters know how to play with them with nuances and know how to subvert them or combine them and artfully.
Gotcha. Thanks.
Hi, I'm Matthew Bouillon from UCSD, and it was a very cool talk. I'm really interested in this system. One question I had is, you have this sort of canvas UI in which people are able to organize and think about things, which is a very interesting choice. And so I'm wondering how you decided for the canvas UI, and in your user study if you found interesting patterns of use that you didn't expect.
Yeah, great question, thanks. Generally speaking, Canvas system are more popular for any ideation tasks. There have been many works about this specifically, and I'd say here specifically, one of the goals was to use tropes in a nonlinear way, which text editors generally kind of constrain the users to work with or in the way of. And Canvas systems, again, allowed more features such as selecting inputs or thinking and organizing your ideas in different ways that a text editor wouldn't allow to.
Great, thank you.
Hi, JD Zamfresco, UC Berkeley. Cool tool. I'm curious, you sort of grounded this very much in tropes and sort of thoughts about storytelling. Did you learn anything about storytelling through this tool or the user study or anything like that?
storytelling, can you define storytelling? Writing
Like
itself?
just like the process of storytelling and like more generally, like are there lessons to be learned about just how people engage in the process and like what are there other ways that we might imagine people engaging in like different parts of storytelling through tools like these, or are there sort of bigger questions about how people approach using tropes or nonlinearities or sort of canvas-based tools like that go beyond what you presented here?
Yeah, right. I see. Thanks a lot for this question. I'd say tropes generally here was a way to probe the way, people would think of stories at a higher level rather than at a very low level of a word level, like text generation would lead you to. And this way of thinking was something that people appreciated and that people felt naturally, that people naturally followed. We have more examples and we have more citations on the paper that I invite you to go look up. Thanks.
Hi, Ace Chen from, Hi, I'm Ace Chen from UC Berkeley. I really enjoyed the work. I think the idea of exploring storytelling is really interesting. And I appreciate that it was not, let's write the story for you, and more about brainstorming and ideation. One thing I'm wondering about is how you imagine beginner storytellers versus expert storytellers using the system, because I see it as both organization and also exploration of these tropes and ideas.
Mm-hmm. Yeah, I think the main difference we noticed between experts and beginners is that experts knew most, if not all, of the tropes that were proposed, or already had examples in mind, or knew most of the examples proposed, or the movies proposed. Whereas beginners sometimes were kind of lost in all these possibilities, but they, at least using tropes, helped them be more confident by just allowing them to access data and to have access to this knowledge that they weren't aware of, and that they were just realizing by using and playing with it. Did I answer your question?
Yeah, thank you.
Very, very quick last question.
Hi, Mohamed Kari from University of Duisburg-Essen. I was wondering, so I think this is one-time use, right, before kind of writing a story. Were there any thoughts on how to maintain this kind of artifact that you're building in the beginning throughout the development of the story?
Yeah, I think it could be possible to have some sort of modular workflow to integrate the use of such framework or the use of tropes at different parts of the story. Here you start from a blank canvas, but maybe coupled with some text editor, for instance, having some recommendations of tropes at different parts of the story, or like adding maybe a plugin to Final Draft, for instance, or any kind of book writing system could be interesting, to integrate these ideas like at different stages of the process.
Thanks.
All right, thank you, John Peck. And also let's thank all of the speakers of today, of this session. And yeah, so that's the end of this session. And yeah, so.
All right. Hello, everyone. Welcome to our session. I hope everyone had a great lunch, and because I'm running slightly late, I figure we'll go ahead and get started right away. So our session is on collaboration today, and our first speaker is presenting VR Roxy, a wide area collaboration from Office using VR-driven robotic proxy. So this work is presented by Moses Sakarahita, and let's welcome our speaker.
Thank you. Hi, everyone. I'm Moses Sakashita. I will be presenting VRoxy, wide area collaboration from an office using a VR-driven robotic proxy. This work was done with Hyunju Ridong-Francois from Cornell University and Brandon from Brown University. In remote collaboration, collaborators often have very distinct environments. For example, collaborators may be located in a spacious laboratory, while a remote participant may only have access to a small personal office. To support such asymmetric collaboration, we propose the design of VRoxy. To your left is the VR user's perspective and top view. To your right is a robotic mobile robot representing the VR user. VRoxy allows a VR user to remotely navigate a large environment from a much smaller space in VR, allowing the user to move around in the virtual environment. The mobile robot on the other side automatically simulates this movement. VRoxy facilitates smooth interactions, mapping the VR user's movement and gesture through a robotic proxy in the large environment. I'm going to unpack what's going on here more in detail in a moment. Telepresence robots for remote collaboration often require a user to drive a robot using a keyboard and mouse. However, previous work noted that the ability to drive the telepresence system divides the user's attention, significantly increasing cognitive load. To reduce cognitive load, prior research uses motion tracking for implicit robot control. For example, Space and remote code use head tracking to automatically control a robot for conversations or design activities. My prior work, Remotion, extends this to enable room-scale collaboration by tracking body movement. However, these systems require symmetric setup where both environments have identical hardware and physical space. Given that environments are often very different, in our work, we seek to explore how we can leverage VR techniques to enable navigation and interaction in large spaces using a small space without having to explicitly control a robot. To explore the design goal, we set up this target scenario where a remote user is in a small office of 2 by 3 meters, while a robotic proxy represents the user in a large space of 5 by 7.5 meters, including a lab, office, and hallway. I'd like to present the key techniques VRoxy uses to achieve wide area collaboration from a small office. First, we explored how we can allow the user to navigate even identical amount of space in VR. One way to allow VR navigation is to use live video of the robot camera, but the robot can be too slow, and the video is unstable when the robot is moving around, which can cause motion sickness. To allow the user to move around naturally and quickly, regardless of the robot state, we design a navigation interface where VR user can see a 3D scan model to quickly understand the environment. A problem with the scan is that these 3D models are static, and the user cannot be aware of where their collaborator is located on the other side. To provide this awareness as the VR user navigates the space, VRoxy visualizes the movement through an avatar using Kinect tracking. The technique presented so far assumes a one-to-one correspondence between the remote and local spaces. I will now present a technique to map small movement in VR to robot movement in a large space, bridging the space discrepancy. To compress the wide space in VR, the user can step into a teleport link for locomotion, allowing the user to move from one place to another place farther away with just one step. The mobile robot simulates the user's location by automatically moving to the destination. Using fixed teleport links defined in the virtual environment, Veloxy ensures that users maintain a consistent position in the physical space without drifting. The interface demonstrated so far shows 3D models that are static, but the system should also support dynamic live interactions in the space. To support this, as soon as the robot stops at the same position as the VR user, Veloxy enables the immersive live view, providing high-fidelity video from the 360 camera attached to the robot. But here's a problem. When the user wants to move around in this area, we cannot turn on the live video because we want to avoid rendering the moving camera. But supporting this micro-mobility is also important. To achieve this, the VR user can move around inside the live view rendering. But the moment that this movement is detected, we pause the live view when the robot simulates the movement. After the robot stops, that's when we turn on the live view video again, allowing the user to take a close look at other parts from a new position. There are other modalities of social interactions that are critical in collaboration. Veloxy supports rendering of social cues captured by Quest Pro, including the user's head and facial animations, as well as pointing gestures using the pointing arm. Combining all these techniques, Veloxy can support collaboration in the target scenario presented earlier. Here is an example. After the VR user completes the tasks with the collaborator in the lab space, the user can exit the room to the hallway using these teleport links in the virtual environment. And enter an office where another collaborator is working. The VR user can see the shared screen and task camera even when the robot is replicating the movement. The VR user can start interacting with another collaborator and review the breadboard. With the help of nonverbal cues rendered through the robot, they can quickly switch their attention to the monitor for continuing the task. Applying the same techniques, Veloxy can also support multiple building scenario, allowing instant travel between buildings. Once the user enters another building using the teleport link, the mobile robot starts parking, indicating that the user is no longer in the building. The user can sit on a chair in another building thanks to the consistency of fixed mapping between the spaces. The robot in another building reflects the notion of the embodiment. As the user leans over the breadboard to have a close look, the robot also leans over the board. The robot can also mimic the movement of looking at their collaborator for discussion. After the discussion, the VR user can leave the table, which is reflected through the robot in the office. We conducted a formative study where we recruited 6 participants, and we found that users were able to navigate and interact in a large environment from a small space, and that they were able to establish good understanding of the physical layout when we asked them to draw a sketch of the layout from their memory. In conclusion, Veloxy allows a VR user to navigate large spaces from a small space using our mapping technique, and can accommodate multiple room and multiple building scenarios. Participants were able to interact with a collaborator in a large environment using Veloxy. Finally, I want to thank all my amazing collaborators, as well as Avatar SDK for providing research license. This work was supported by NSF and Nakajima Foundation. I'd like to also announce that I'm on the job market, so please reach out to me or talk to me later if you have any opportunity in mind. So with that, thank you so much.
Excellent. So we have some time for questions, and while other audience members join, I have a question. So yeah, this is cool work. Thank you so much for the talk. I'm quite curious, have you started to look at all if the robot had other types of movements, such as arms, or maybe they could fly around? Have you considered what the implications might be for your system?
Yeah, thank you so much. That's a great question. That's exactly what we are exploring as the next step, because the robot right now doesn't have any physical interaction with to manipulate, for example, physical objects here and there. It has only capacity to point at a physical object. So adding robotic arms to be able to physically manipulate and have, more interactions with the physical world would be a great addition. So thank you so much.
Excellent, thank you.
Hi there, great work, Mose. Ian Arajo from Harvard University. One question I had, when we present papers, we often present the final project of the interaction. The teleport thing seems really cool to me. Was that the first thing you tried, or did you go through some dead ends in your prototyping process?
You mean the how we, design our locomotion system, right? Or
How you arrived at this teleportation
Right.
interaction, yeah.
Yeah, that's right. So we explore some ways to, navigate in a large environment, like a virtual space, for example, like using controller to navigate, and then map the movement. But it's not very intuitive, and again, it causes some cognitive load to kind of, explicitly control and, navigate in a space. And also, previous work suggested that if you kind of use walking, natural walking, it helps you to create like a cognitive map of the space. And so we combine both like prototyping and user testing, as well as literature review. And yeah, thank you.
Thank you.
Let's thank our speaker one more time. All right, next up we have Haijun Zai presenting Crosstalk, Intelligent Substrates for Language-Oriented Interaction in Video-Based Communication and Collaboration.
All right.
Let's welcome our speaker.
Okay, so let's talk about video conferencing. Video conferencing is everywhere, right? We use it for our collaboration and education, and also just connecting with our friends. But the fact that it's everywhere doesn't mean it's perfect, right? And I want to do a quick show of hand just to remind us how terrible the user experience is. And just raise your hand if you have accidentally unmuted your microphone in the past and someone told you to mute yourself and you scramble to find the mute button to save your dignity. Raise your hand. Is that everyone? Okay. So the next one will be like you want to share something interesting, but it's taking a long time to find it. And you got anxious because you feel you're getting boring and then you're wasting everybody's time. Raise your hand if that happens. Everyone, right? Next one is you saw something like this happen to someone else and you really want to step in to help them. Raise your hand if you want. Okay, you guys are all considered human beings, but I see some of you are not raising your hand. So, we all need help and we all want to help, right? But then why video conferencing applications just remain oblivious to all these scenarios? Can they be more considerate and then, help us when we really need the help? So to answer this question, let's take a look at a concrete video conferencing example. And imagine, you're having a conversation with your colleague. You know that they are traveling to San Francisco for a conference. And you said, you should go check out the Golden Gate Bridge, which is really cool. But if they don't know where it is, you're probably like, I'll probably show it on the map, right? But then if you realize that, that's going to take you a while to find the map, right? Open the browser, go to Google Map and type the location and then, pull everything up. You probably say something like, give me a sec, right? Let me pull up this. And then finally you go through all these things and you're like, you want to share it, but then you realize your friend hasn't enabled screen sharing. So you're like, hey, enable screen sharing for me. And then they probably like, oh, I'm sorry, right? I haven't done this. And then they will, at the same time, trying to figure out where the screen sharing permission is. And then finally, you will be able to share, right? That's the process. And, during the conversation, they may have something they want to share, right? So they will probably like, can I share something? And then they will take over the screen sharing. And this can go back and forth because we all have something interesting to share. But in reality, each turn taking is not as smooth as this animation, right? It will take a lot of time and coordination. So what's really going on here? Effective communication builds upon shared understanding of the context. But outside of this tiny window on your computer is the rich physical and digital context that we do not share with each other, right? And video conferencing applications provide screen sharing, but it's a very limited mechanism, right? And often result in really frequent, context switching back and forth. So in crosstalk, instead of, using this video-based context establishment, we turn video conferencing into a collaborative space where the shared content is, they are persistent in the space to reduce context switching. Our second and key insight is that we are all considered human beings, and we are aware of the lack of shared context. So therefore, when we realize there is an upcoming context mismatch, we will often try to compensate it, through verbal conversation by, informing them the actions we will do. Right? And this presents an opportunity for the meeting materials sort of to listen to the conversation and provide context-aware assistance. So let's take a look at how this is realized in crosstalk. So this is the crosstalk interface. On the top is the attendee panel. In the middle is the shared space. And at the bottom is the transcription panel. So in this particular case, these two people are talking about where they should travel from Toronto. And they may say, oh, we should go check out New York. New York is pretty cool. So as they are saying that, oh, we should go to New York, the map panel listens to the conversation and prompt the user, hey, do you want to add another panel, which is New York? And then the New York panel will be, if you accept that recommendation, you can create a New York panel. And then you may keep saying, there are a lot of interesting museums in New York, and the New York panel will realize this potential context switch and then search the museum automatically and prompt you to, accept that recommendation. So here's another example. So in my meetings, I often share papers with my students, right? And when I share papers with them, I usually have a particular phrase or figure in mind that I want to point them to. But finding the paper itself is already hard, but then I have to scroll the paper back and forth to find it, right? So for example, this is Mark Weither's technology would disappear into the background for psychological reasons. So in crosstalk, the PDF can listen to the ongoing conversation and recommend relevant sections and paragraphs based on the conversation, and visualize these recommendations on the slider bar. The intensity encode how similar how relevant it is, and then I can hover on it to preview the recommendation or click it to directly jump to that section, right? So these interactions are possible because in this shared space, we treat all these materials as intelligent materials, which contain three key components. So each material, like whether it's an attendee panel or a map, contain content, actions it can do, and the context. For example, for an attendee panel, the content will be, who this person is, their contact, and all the other information, and the actions this person can do, or the context record the content they have said. And all these are described using natural language. For example, mute or unmute, change host, their functionality is described using natural language. And for a map, it's the same thing, right? The content is the current location, the action are the location search or route search you can do. And by describing all these using natural language, it really enables this semantic searching. So basically, crosstalk, take your conversation as input, and relate its conversation as input. And then just find all these materials and just loop all these materials through their content, their action description, their context, and find the most relevant material and action you can do, and then give the user the recommendation. And then the user can accept the recommendation or not, and that action is recorded as interaction history. So this way of basically using natural language to describe and record these things is our way of building this intelligent behavior. And it's different from traditional intelligent application where you have to define the intelligence of the application level, but here the intelligence is specified within the material, right? So you can imagine you have your own material, as long as you describe all the things it can support, you drag and drop into this environment, and then the user can intelligently interact with it. So here's another example. So this is somebody is doing a screen sharing presentation, then I'm looking at the screen sharing presentation. So in crosstalk, screen sharing is persistent. It's not transient. Like, it's like when you stop it, it will be like preserved. But it's preserved on the presenter's side, right? And if the presenter, think, this is going to be useful for the follow-up discussion, what they can do is they can drag and drop this, recorded screen sharing session into the space. And once it's in the space, it's, basically visible to all participants in the call. And, seeing this, right, I can say, hey, I have a comment for the motivation section of this. So similarly to the PDF, what Crosstalk can do is basically help you find the timestamp based on the context. And you can hover on the, you can click to get there. Or if you're like, I don't want to disrupt, everybody else's viewing experience, what you can do is you can just drag that frame out as a separate material, and then you can annotate on it just to facilitate the discussion. So here's another example. Imagine I'm teaching with this tool, right? I can leverage Crosstalk to turn a question into a live polling question, so the students can interact with it. So we have a full design space in the paper. I encourage you to check it out. But so what didn't work? So when we were building this, the assumption we built upon is people will think aloud. And we observe people think aloud, especially when they run into this context mismatch. But sometimes, their conversation happens as or after they are doing the actions, right? And when we were doing this, large language model wasn't a big thing, and that was a big problem for us. But you can consider now with large language model, you can sort of take the user's action as context and predict the following actions, right? So that will still be useful for them. Another thing that we find in our user study is not all users want an AI listening to them, right? Some are really concerned with the privacy and the data being saved. So I think for this, new social protocol is probably needed, and how to inform the user how the data is used and let the user control whether they want this layer of intelligence. And also, I think the embodiment of AI will be super interesting. Like in Crosstalk, we don't embody AI, right? But you can imagine there is this, intelligent facilitator that's there, right? So then you can sort of know, okay, this roughly probably behave as a meeting facilitator. Okay, so what's our takeaway, right? So stop seeing video conferencing as just a video chat. It's an extensible and collaborative space that is enriched with language-based intelligent materials. And the AI will make these lightweight recommendations, and the human can use lightweight interaction to make the actual UI change. So that's Crosstalk. I'm happy to take questions.
Oh, all right. Yes, go ahead.
Thank you for the great talk. I'm Seo Pei from UCLA, and I'm curious that during the need finding study, have you find the personal preferences across individuals? Like when they talk about something, did they say that some of them want some visuals to help them? Some might just want to remain
Yeah, so my students will know who I'm talking about. But when we did the formative study, we collect all the video recordings we had during our the whole pandemic and other groups video recording. One of my students, he's really feel that just when he was setting up, the silence was awkward. So he hums and makes this little noise, and he didn't really think aloud. And I've been really curious why he made that. And then I asked him, that's his, he didn't really think aloud, but he was trying to fill the silence, right? Some people are more really think aloud, okay, I'm opening Chrome right now. Let me find a tab. Let me, some people are more verbal, and they communicate more. But you can, I think that's, without intelligence, right? You can imagine if they know there is this intelligent agent listening, maybe they will do more. So
Yeah, thank you.
And let's take one more question as we switch speakers.
Hi, I'm Jimmy Lin from Google. Really interesting work, really great. I was just curious, how, you had a whole list of intelligent meeting materials with, their related context and actions and stuff. How easy is it to create new material and to add it to your system?
So this is a prototype system, but we will explore the mechanism, right? But the idea is, imagine you have a web component, right? And this web component, let's say Google Doc, right? For every single action, if you can say, copy, paste, or bold, or italic, you can give a description, and then import it, and hopefully, the the crosstalk and will know which button to click.
All right. Okay. Thank you.
Awesome. Let's thank our speaker one more time. Excellent. Next, we have Vivek C. Nair presenting our Best Paper award-winning paper, Going Incognito in the Metaverse, Achieving Theoretically Optimal Privacy Usability Trade-Offs in VR. So let's congratulate our speaker on his Best Paper award. All right, it's all yours. Take it away.
Thank you. All right, so I'm going to be talking today about MetaGuard, which is a system that we like to call the incognito mode of the metaverse. I'll explain what that means in a minute. This work was a collaboration between UC Berkeley and TU Munich, and my co-authors are Gonzalo Munilla Garrido and Don Song. So I want to take a step back and discuss privacy risks in the metaverse. And the story actually goes all the way back to the 1970s, where researchers were just beginning to realize how much your motion patterns say about you. So there's this famous study from 1977. These two authors, Cutting and Kozlowski, took a bunch of people into a lab, and they attached little points of light all over their body. And then it turns out that if you show people just these points of light, so the silhouette disappears, and you just watch people moving around, people were able to name the person they were looking at just based on their movement patterns, right? So this is not something we practice, but it turns out we can just intrinsically recognize our friends based on how they move, not only recognize them, but learn a lot of information about them. So this is something we've known for like going on 40 years. But jumping forward now to virtual reality, what do we have? Well, we typically have a headset, we have two handheld controllers. Those are points on the body that are being tracked in 3D space. And then you're tracking the motion of points on the body, right? It's basically the same type of data that we've known for over 40 years can uniquely identify individuals and profile a lot of information about them. And in VR, that data is streamed not only to the VR application, but in the case of a multi-user or metaverse application, that same data is actually streamed to a server and then on to all of the other users who are in the same virtual world with you. So this is a potential privacy concern, and in fact, recent studies have shown that the same motion capture data that is tracked by VR devices can be used to accurately infer a wide variety of personal information attributes about the VR device user just based on their motion patterns. 3 studies I want to highlight in particular. There's a 2020 Stanford study with 500 users that showed that they could uniquely identify all of those users with head and hand motion. More recently, we had a study in Berkeley, 2023, that took 55,000 users in a game called Beat Saber, and again, uniquely identified all of them based on head and hand motion patterns. And then a third, a Berkeley study in 2022, which showed that adversarial VR programs, that ones that actively manipulate the virtual world, can learn even more information about VR users beyond just their identity. So now when we think about privacy threats in VR, these might not seem particularly unprecedented, and in fact, we do have corresponding privacy risks on the web. We have sort of tracking cookies and other browser fingerprinting, things like that. But over time, they've developed a suite of defenses, and users have gotten used to having some tools at their disposal to take back some privacy, whether it's something like a VPN or incognito mode, right? That's the inspiration of this paper. But the reason those tools are possible on the web is because you have access to fine-grained permissioning, right? You can think about a mobile app where you can say, well, this app needs to have my location, but I don't want it to have my contact list. In VR, that turns out to be pretty difficult because with the same exact motion data that is fundamentally necessary for a game to operate or any VR application to operate is the same motion data that can be used to infer private information. So there's no fine-grained separation there. And that makes it pretty tricky to think about what the equivalent of an incognito mode would be in a VR application. So that's what MetaGuard aims to solve. And the way we do that is through a system called epsilon differential privacy, which is a mathematical framework that essentially allows one to quantify the privacy improvement given by adding a certain amount of noise to a private variable. And you can quantify the maximum probability that a hypothetical adversary would be able to distinguish between a data set with and without a particular target user. And it's generally not something that makes sense in the streaming setting, so we had to use a few tricks to get this to work in virtual reality. So what we did is we implemented a system called MetaGuard as a Unity plugin. So this is something that you can just insert into any Unity-based VR game or application. This is a mixed reality photo of me demonstrating the tool. And essentially, when you insert this into your VR system, you can just press a button on your controller and bring up this menu. And with a flip of a switch in VR, you can go incognito. Just like in a browser, you can click a button and go incognito. So what happens when you flip that switch is as follows. So the first thing that happens is the system tries to get a ground truth measurement. It takes the distances between various virtual objects to try to estimate your true height and your wingspan and room size and these various dimensions, which in practice we found are how these VR identification and profiling attacks typically work, is by measuring certain unique anthropometrics that can be used to consistently identify you over time. So you get a ground truth, and then you pass through those values through differentially private noise functions. In particular, there's a function called the Laplacian noise function. And when you pass that through, you end up with these fictitious measurements, like a fake height, a fake wingspan, that make up a faux identity. And so the goal of MetaGuard is basically that when an adversary tries to make these measurements using virtual objects, they'll be measuring sort of a fake user, which is not really you. And the way that works is basically in every Unity game, you have this virtual object hierarchy. And when you turn on that switch in MetaGuard, these intermediate objects are inserted into that hierarchy that basically transform the virtual world in such a way that if the game or another user were to try to measure avatar characteristics that correspond to some of these sensitive dimensions, they would always observe the differentially private fictitious values rather than your true measurements. And importantly, we designed these transformations in a way that preserve certain 0 points that are important for usability. So for example, if I stretch my arms out, then you're going to get a differentially private measurement of my wingspan, but I also retain the ability to touch my hands together, and that allows me to interact with objects in the virtual world. And the nice thing about differential privacy, and this is what inspired the title of the paper, is that there is a provable optimality between mean squared error experienced by the user and the level of statistical indistinguishability that you get. So if you define usability in VR as proportional to the squared error, right, the squared difference between fake height and real height, for example, then by that definition you get provably as much privacy as possible for any given level of error that a user can tolerate. So going back to these 3 studies, we used these 3 studies to form the benchmark of our system. And we got all of the original user data from these 3 studies. And we simulated those sessions in a virtual environment using Unity with our MetaGuard extension that we had built. So in other words, the result is exactly what data would have been observed if the users in these 3 studies had originally been using the MetaGuard system. And what we found is that MetaGuard is actually very effective at obscuring the specific dimensions that it attempts to hide. So a non-adaptive model, just repurposing those existing identification model to attack those users, has a significant degradation in success rate. So in particular, you lose the ability not only to identify and profile a user across sessions, but also you lose the ability to make a lot of those sensitive attribute inferences that could previously be made. So that's all. I'm happy to take any questions. Thank you.
All right, while we wait for audience member questions, I have a question. So this project's super cool, and thank you for the very engaging talk. I was wondering, are there other attributes of users or their actions in environments that you could see being perceived later on? So it could be the sequences of words people use, or even their longer term actions in environments that maybe over time could be identified.
Yeah, certainly. I mean, we designed the system in a way that is fairly modular. So ideally, if there is some attribute that we didn't think of, it should be fairly easy to augment. But one of the challenges with this system is that it works really well when you have head and hand tracking, which current VR devices do. Once you have full body tracking, the next generation, which have 20 plus tracked locations on the body. Engineering all of the relationships between those points that could be sensitive, it's a much bigger engineering challenge. So we're working on future approaches, deep learning-based approaches that can try to automate some of that process of discovering what are all of these features that could be sensitive and then protecting all of those features. Great question.
Hi, Yifei Cheng from Carnegie Mellon University. I have two questions. The first question is, how do you communicate this concept to a user? Did you run into this as a potential problem? You know, like, okay, maybe, like, what does it mean that the mean squared error of my height is off by like X? Or what does it mean to be low or high? Like, that's very, is that something that you found was difficult for someone to have an intuition about, or what's your sense there?
Yeah, I mean, the thing we realize, right, again, the inspiration is incognito mode in the browser. And the thing we realize is the average user has no idea what that means, right? That I'm, you know, disabling my cookies between sessions, that I'm not maintaining the history. They have basically some idea that this is a more private version of the same experience. And so that was the baseline goal, is if you are that type of user, you can just flip a switch and have a pretty good experience, which is much more private than the default. Then we do dive into some more customizability. So there's a slider here that changes this variable epsilon in differential privacy, basically adjusts the usability versus privacy trade-off. So there's ability to dive in deeper, but we don't, you know, we still simplify it in the interface. So we just say lowest privacy, medium privacy, high privacy. This is sort of the level of understanding that's necessary to use the system effectively. The details of noise behind the scenes. It's not clear that user needs to understand exactly what's happening. Of course, they're welcome to, but it's not clear that that would affect their experience, not understanding the details.
Hey, since there's someone else behind.
All right, let's take one more question as we switch our speakers.
Hey, Tucker from CMU, thank you for a wonderful talk. I'm sort of similar to the first question. Curious with the, improvements in on-headset hand and finger tracking, where you have much finer grained biometric data. Do you see different obstacles to maintaining meaningful privacy and meaningful usability with these things where small changes might make a big usability difference?
Yeah, I mean, the idea with differential privacy, and the reason we didn't even do detailed new user studies on this, is that whichever attribute you're concerned about, if there is any level of noise tolerated by the user, you can guarantee that you're going to get as much indistinguishability as possible for that level of noise. So it's almost immaterial to say how much noise can a user tolerate. The idea is if there is a potential to gain privacy in this attribute, you will gain as much as necessary. And so that's the idea with the differential privacy version. As I mentioned, we're working on a deep learning version that may be in practice more suitable to take advantage of all of these small differences that are not as obvious as height and wingspan and things like that.
Thanks.
Let's thank our speaker one more time. All right. Next up, we have Noor Hamad, who is looking for internships this summer. So if you listen to her talk very carefully, please talk to her after. And the talk is The View from Mars, Empowering Game Stream Viewers with Metadata Augmented Real-Time Streaming.
All right, thank you so much. Just a second, it seems to be broken on my side. I'll give it a second. Here we go. Blinking, it's blinking. Huh? I'm able to mirror but not extend. How's it going? Happy Halloween, everybody. Let's see if that works. All right. We're good to
Let's
go.
welcome Noor.
All right. Thank you. So hi everyone. My name is Noor. I'm a PhD student at the HCI Institute and the Center for Transformational Play at Carnegie Mellon. I'm here representing my co-advisors, Eric Harpstead and Jessica Hammer, to present our work, The View from Mars, Empowering Game Stream Viewers with Metadata-Augmented Real-Time Streaming. So this is Mars. It's a scalable architecture that we created to enable metadata-driven interfaces for game streams on the Twitch live streaming platform. Mars lets us do a few cool things, which I'm excited to share with you today, but it's important to talk about Twitch first. It's a live streaming platform which has greatly increased in popularity, especially during the pandemic. And even though Twitch is home to many different genres of streams, many different types of streams, game streams remain the most popular type of content on the platform, and it's what we'll be focusing on today. And like I said, Twitch has seen this exponential growth in viewership, but the viewer interface itself has remained largely unchanged. This is what you would see if you were to hop on Twitch. There's always pretty much a game view, there's a camera view of the streamer, and a text chat where viewers are able to interact with each other and with the streamer. And this setup restricts viewer interaction and does not accommodate the varying needs of viewers, such as accessibility needs, the need to have contextual information, or even novel gameplay experiences. And Mars solves these limitations to the current live streaming interface by letting us create what we call game-aware interfaces. These are interfaces that are data-driven viewer-side interfaces which are closely integrated with the game content being streamed, but don't make assumptions about the underlying game nor use external data sources. But what does that really mean? So game-aware, I'm going to talk about the core features that make a live stream game-aware. The first being viewer customization. So just for a little bit of context, for all the videos I'm going to show through the presentation, on the left side you'll see the streamer view, so this is the game itself. And on the right is the Twitch viewer interface with the Mars overlay enabled. And this was all recorded on a single computer, but you'll still be able to see the latency between the game that the streamer is playing and what the viewer sees. So in a traditional Twitch interface, it's difficult to accommodate the individual needs of viewers, partly because viewers are not allowed to interact with the game content independently of the streamer or other viewers. So anything the viewer wants to see happen, such as turning on an accessibility feature or seeing a different part of the game, all of that has to go through the streamer. But Mars is an architecture that enables different overlays to be rendered from a single Unity game, which thus empowers individual viewers to independently augment their experience. So that video was from a visual novel game that we developed at the CTP called Bloomwood Stories. And we chose this demo to illustrate how multiple users could have personalized front-end experiences with the same game stream. So on the left, like I said, is the streamer view. And as you can see, it's a very text-focused game where the dialogue choices are kind of the primary mechanic with which you interact with the game. And on the right, we have two viewers, both of whom have different needs, which would be hard to meet in the traditional Twitch interface. So viewer one uses Mars for visual accessibility features, where viewers with visual impairments can have their needs met without the streamer's intervention, even if the base game does not provide the accessibility feature in question. So they use the overlay to manipulate the text, and in this screenshot there, increasing the font size, changing the font color, and changing the font type as well. Viewer 2 has different needs from Viewer 1. They're not native English speakers and want to understand the game's dialogue at their own pace in their own native language. So what they use the overlay for is to change the language of the text. And another thing they're able to do is page back and forth through previous dialogue that the streamer has already went through in order to better understand the in-game dialogue that has passed. So the second core feature of a game-aware experience is what we call live data updates that are specific to the session being streamed. So in the previous demo, what viewers are actually manipulating is text, and there's a few ways we could have implemented that, but game-aware overlays let us do a bit more. Another critical consideration when working with live stream systems is latency. The broadcast latency between the stream and what the viewer sees can be anywhere from 4 to 12 seconds. But with our architecture, we support real-time data updates sent to the overlay. And this powers the game-aware experience and gives the front end everything it needs to keep up with the game video feed. This also includes automatically localizing the metadata to screen space and time on a per-viewer basis. So this ensures that the data is live and up to date regardless of latency for all viewers. And not only that, but this live data emphasis means we can render metadata that is off-screen, or rather data that the streamer themselves cannot even see. So this demo is what we call Invisible Maze. You could think of it as like a floor is lava type game. And on the left, the streamer is trying to control their character, and the goal is to get across the screen, but they can't see which tiles are safe and which tiles are lava. So on the right, we have the Mars overlay, and viewers are able to see the safe tiles marked in yellow, along with some additional hints on how to complete the puzzle that we laid out in this level. One thing that's worth noting, and it's hard to see in the demo, but the maze is actually randomly generated every time you start the game. So everything you see on this viewer side follows this live data update philosophy and is rendered from the relevant moment-to-moment metadata. It does not use external data sources which tell the front end what the map might look like, nor does it use any external tools like computer vision to figure out what the rendering layout is. The final core feature of a game-aware experience is real-time dynamic motion. So the 2 example demos I showed you highlight some of the exciting features in Mars, but some of the previous systems that we're really inspired by, which you could check out in the paper, also support some of the same features. But our architecture is such that we can support more complex games, such as ones that have 3D assets and have a moving camera rather than a fixed camera. And creating such a system for real-time interactive overlays for multiple genres of different levels of complexity required a substantial technical pivot from previous approaches. And our approach to metadata tracking in Mars and rendering lets us generalize our approach to multiple game genres. So the demo you just saw is of a tower defense game. And in terms of in-game features, it does capture the viewer customization and live data updates that I talked about. But it's a different genre of game that's more complex, because playing a tower defense game requires the streamer to move around the space to update towers. But the Mars viewer overlay still correctly localizes to the correct screen space and provides the same affordances as the previous 2 demos. So to summarize, I just showed you 3 core pillars of a game-aware experience. And each of these core features tie to specific aspects of the Mars system. So that's what Mars can do, but how does it actually do that? So this is the full Mars architecture. And on the left, we have our Unity side, where there's a Unity library that we make available, which exposes metadata. And it does not care how the metadata is used on the front end. And this is also where we put our screen space localization algorithm. So that metadata is sent through a middleware, which is where we index the metadata over time. And we use Redis for this, and it is hosted on an AWS EC2 instance. Finally, the front end, developers are able to use the incoming metadata in any way that they want using any modern web framework. And this is powered by Twitch's extension API. And this is also where we do the time synchronization algorithm, where we estimate the delay to the streamer and retrieve the relevant data frames from Redis. So in creating Mars this way, we offer flexibility to both game developers to expose what metadata they want and front-end developers to render the metadata in any way that they choose. And we're really excited about the future of Mars, game-aware interfaces, and the potential to support this distributed ecosystem of game developers, front-end developers, streamers, viewers, moderators, researchers, all across this tech stack. And on that note, I'm actually going to conclude with a plug for our follow-up study, which is ongoing right now. Now that we have Mars working, our next step is to work directly with the affected stakeholders that I mentioned to improve the features, but also to explore the design space afforded by Mars. And if you're interested in knowing more or want to take part in this study, feel free to contact me, but also feel free to check out the QR code and the survey link, and the link which both take you to the screener survey. So thank you very much for listening, and I'll be happy to take your questions now.
Hi, Jeremy Warner at Apple. So this is really cool. Thank you for your talk. One of the things I was also thinking about was kind of viewers interacting with the stream, or something like Twitch Plays Pokemon, where there's kind of a circular effect or influence on the game itself from viewers. So I was wondering if you were also thinking about something along those lines.
Yeah, thank you. That's a great question. It's like a really big source of excitement for us, because that's kind of our immediate next step. Some of the systems we were inspired by are audience participation games like Twitch Plays Pokemon, and that really what it is bi-directional information. So that's the next core piece that we want to integrate. And one thing that is a random feature, but we're really excited about things like region tagging, a viewer wants to tag a particular thing, so that you're able to localize some of that information. So yeah.
Cool. Thank you.
Thank you.
And let's take another question as we switch speakers.
Hi, Qisen from UC Santiago. Very cool work. And my question is, have you considered to help the viewer know the intent of the streamer's operation? Based on my experience, sometimes in mobile games, the streamers will sometimes look at the scoreboard or look at the minimap, but sometimes it will only take a few times and a few seconds, but the but the viewer will have no chance to know what the dreamer want to do next. So I want to know your thoughts.
Yeah, so that's a great question. So I would say that's kind of like a contextual information piece of like letting the viewer make sense of things like whenever they're ready, let's say. Another piece of that I think that affects is like what we call drop-in spectatorship, which is very common on Twitch. People drop in and out of streams, but they want to be able to make sense of information whenever they want. So that is actually a core consideration for us, and it is, we think it's possible. And that first demo I showed you kind of has that, which is like you're being able to page back and forth in dialogue. So even if the streamer moves past like a menu or something, you're still able to access that information.
Okay, thank you.
Thank you.
Awesome. Let's thank our speaker. All right, our next speaker is Hai Dang, presenting WorldSmith, a multimodal image synthesis tool for fictional world building. Hai is in the final year of his PhD, and so he's going on the job market this year with this very exciting work. So whenever you're ready, take it away.
Okay, so today I will be talking about the WorldSmith, which is the outcome of my research internship at Autodesk Research this past winter. And the project is basically about world building with a generative AI. So when people build worlds, they have stories they want to tell. And this can be conveyed either through artwork or through writing. And in the scope of my project, at least, I want to focus on the creation of visual artwork as part of the world building process. And as you can imagine, there are a lot of tools for world building, and these tools create the maps and the scenes procedurally based on existing libraries of assets and items. But if these items and assets do not yet exist, it's quite time-consuming to create them. On the other hand, we have generative models such as DALL-E and Midjourney that allow users to create images with just a short description of the content of the image. However, if you want to use these types of systems for world building, this can be quite complex because users, they require users to think of the world beforehand as a whole, even before they started the world building process. And iterations on the text prompts are the only ways of changing the image. So how can we do better? We introduced WorldSmith to support kind of an iterative world building process. And in our UI, we essentially have 4 parts, including the global tiles composer that lets users blend in different elements of the worlds. And we also have a detailed editor that lets users focus on specific elements that they want to include in their worlds. We also have a view of all the generated images and a tree view that allows users to revisit the past interactions. And so we also conducted a formative study to see how world builders are envisioning the worlds. And while the overall setting of the world, such as the time and the mood, is fixed from the start, we see that people tend to think of different elements of the worlds one at a time. So they build the worlds piece by piece, and once they have figured out all of the core elements, they try to blend all of these elements together into an entire vision. So let's see how WorldSmith helps users in building or envisioning the worlds. Here's a quick demo of how this blending process actually works. As you can see, the user can select, recompose, and resize the elements of the envisioned worlds, and all of these elements are contained as individual image tiles. The users can provide a quick description of how the world should look like, and with a click of a button, they can blend all of these tiles together. And of course, they can also, again, recompose all of the image tiles and render the alternative versions of the worlds. Now let's have a closer look at the detail editor and see how users can work with this view to work on the specific elements of the world. User can provide a description of the overall world. This is very similar to the text prompt that you would provide to DALL-E and Midjourney. But on top of that, we also allow users to mark regions in the image to describe what should appear in the region. So in this case, we want to illustrate a dragon's head. And sure enough, the model would suggest different generated results displaying the dragon's head, exactly at the position where the users maxed out the dragon's head. And here's another result. But more generally, we implemented 3 different interaction modes that allow users not to only use text prompts to generate the images, but also to combine text with regions as demonstrated before, And also, we allow the users to draw and translate the rough sketches and, render that into a more high-fidelity rendering. And as users progress in the world-building process, they also might want to revisit previous iterations. As you can see from the root, there is a separate branch for each of the image tile. And when users generate a new image, all of the text prompts, regions, and sketches are automatically saved in this tree view. And as the user scrolls through the entire tree, they can retrace previous drafts of their world building and edit them. So let's say that the user is not yet satisfied with the dragon that they have previously created, and they wanted to add a new asset. So one thing that they can do is they can add a new node to the tree, which represents a new canvas and a new asset, and merge that asset into their previous creations. And here we create a knight in a dark armor and place that knight on the back of the previously created dragon. And again, we can use the regions and sketches and the text prompts to iterate on this knight until we're happy with the results. And once we're happy with the results, we can drag that asset back into our previous creations and the image, and then blend all of these elements together to have the knight on the back of the dragon. So through Wordsmith, we essentially conceptualized two new expressive prompting techniques. One of the prompting pattern that we have identified here is what we call hierarchical prompting. Essentially, this means that we attach prompts to different layers of the composition. At the very bottom layer, we have the blend layer to merge all of the image tiles together. But users can also generate images by attaching prompts to different image tiles. And finally, text prompts can also be combined with regions and sketches as shown for even more control over the output. And the second prompting pattern that we identified is spatial prompting, where expressing spatial relations through natural language is often ambiguous. We propose spatial prompting as a way for users to specify spatial relations through their direct input. So for example, they can move tiles across the canvas to prompt the image generating model. Or they can also prompt the model by exactly drawing the sketches in the regions and the positions that they want the elements to appear. Of course, we also conducted a user study with 13 participants here to evaluate the overall usability and the usefulness of Wordsmith. And in our study, we identified differences in how the way that users phrase their prompts when they describe the scenes as compared to the way they describe the regions and the sketches. And also the participants alternated the workflow, going from kind of like this broad vision to fine details, and then back from the fine details to this global composition. But here we refer to our paper for more details. As you can see, these are some of the worlds that participants have created, and participants have also compared the world building process using Wordsmith with experiences without using a generative AI. And instead, here one participant said that in the past, frequently I found myself searching for compatible tiles, for instance, connecting streets. However, with this system, I would simply provide sufficient space between the tiles and let the system determine the best way to merge them. In another instance, one participant specifically noted that Wordsmith's proposed workflow closely resembled their regular workflow. So I do more fine details and then go, oh wait, I should actually do something a little bit more broad. So the workflow wasn't anything new. It was kind of more a natural flow for me. So finally, here are the things that I want you to take away from my talk. We introduced Wordsmith to create fictional words with a generative AI. And through Wordsmith, we essentially demonstrated two new expressive prompting techniques, namely hierarchical and spatial prompting. And this work also shows that we need to integrate more direct interactions when prompting to allow users to better iterate on the worlds, because creating interesting artwork is rarely a one-click process. Okay, and that's it. Thank you for your attention. And I also want to thank my co-authors, Frederick Brody, Josh Fitzmaurice, and Fraser Anderson for supporting me throughout this project. I'm happy to take the questions.
Hi, this is Bala Kumarvel from Microsoft Research. Really cool work. I was curious, did you find any interesting patterns in which users extracted and reused the generated content / characters across the world building process? Interesting patterns. So one thing that
I haven't mentioned that during this talk here, but we focused only on 4 different image tiles. That was just limited by the time constraints of our user study, which was 60 minutes. One of the participants said that in order for them to build the worlds, they would actually want to have unlimited numbers of image tiles so that they can create all of the different assets and then kind of like put all of these elements together to form the entire worlds. But other than that, I guess participants in our user study were focusing on like building their stories first as they were envisioning the worlds, which was quite vague in the beginning. So yeah, the entire process of iterating on one of the image tiles was like how they developed the worlds. So they started off with a very vague idea, they iterated on it, they tried different things out, and then in the end they were like, oh, this is what I was actually looking for, so let's see how this looks like when I blend it all together into a world. Yeah.
Just a quick follow-up. So how did the generation affect, so because one of the user comments was like, oh, I just had the tiles close enough and let the system do the blending. So did the generated artifact influence the way users were thinking about building the world? Like, or was it always like users had a specific idea in mind and they just kept generating till they got that particular idea?
So like I said, this was informed by this formative study where we found that users were actually thinking about very specific details of the world first. So for example, in this world building process, they wanted to have a dragon in it, and they somehow wanted to have this fantasy theme and a knight in it. And so they were just thinking about individual elements first. And kind of like this blending process was minor to them, I would say. Because I said, like, as long as I have all of the elements that I want to include in the world, how these elements are blended together is kind of like a nice to have. And if the system takes care of it, that would be nice, yeah.
Thank you very much.
Great, let's take one more question as we switch speakers.
Brandel Zetranek from Apple. This is amazing work. I have a question about fidelity. You have very low fidelity inputs and then very high fidelity outputs. I'm wondering if you have the ability, or if you've explored having the ability to show intermediate levels of fidelity. In practice, in film effects, visualization, advertising, people use sketches not just because they're fast, but because they're also conceptually open-ended enough that people retain that flexibility. The images that you create with the tiles are already fully resolved. Have you explored, or would you be able to use more coarse-grained things for the purposes of an iterative and progressive ideation?
We haven't exactly explored intermediate representations. We were actually going to the other side to look at how we can allow users to blend concepts that are not necessarily related to each other. Especially for fictional world building, you'd sometimes want to build worlds where you try out different elements that are not necessarily, for example, if you build fantasy worlds, you might want to include a dragon, but I don't know, for some reason you also want to have a futuristic car in it. And so we are still trying out to find ways and allowing users to combine vastly different ideas. Yeah. Oh, okay.
Awesome. Thank you so much. Let's thank our speaker. All right, next up we have Jianjiang Li presenting Wavo ID, robust and secure multimodal user identification via multimillimeter wave voice mechanism. And Jianjiang is an assistant professor, third year, potentially looking for PhD students at the University of Colorado at Denver. All right, take it away.
Yeah, thank you for a nice introduction. Good afternoon, everyone. My name is Zhenxiong from University of Colorado, Denver. And the topic of my presentation is related about robust and secure multimodal user identification via the millimeter wave voice mechanism. Currently, we know sound, voice has been widely used in our user interaction method because it's super convinced, and also it's very easy to use, little user cooperation, everyone like it, high user acceptance. And it's already become widely appeared in many, many important domains. And the global market size, by estimation, will be reached over 27 billion by 2026. and due to its very, very unique advantage and benefits, have been applied in many of our interaction servers, like voice assistant, speech to text, customer server, and also intelligent drive. Once we talk back to our daily life, I guess everyone has hold such device, like smart speaker, smart watch, maybe even your smart vehicle, and without saying your smartphone. But however, I'm a little from the security background, a little different from our previous presentation. My concern is how could we protect our voice user interaction? Usually, typical, our solution is called user identification. Here, voice identification. And if we call general, like biometrics. The way is that the mechanism behind that is we try to capture the very unique characteristic about users, no matter from biological or behavior, try to find some unique ID to representing some password to identify benign user and also against some malicious attack. But however, currently in the user authentication, it has several problems. For example, I guess everyone has such experience. Maybe your smart speaker is very, very vulnerable to ambient noise. If the noise around you is very loud, it cannot work very well. It's very interference to the ambient environment. Second, it's called a replay attack. That is attack, we can assume attack can recall using some electronic device, record your voice in advance, and then replay this recorded voice directly to your device, and in that way to spoof this authentication step. Last one, adversary attack. If you're familiar about our AI or machine learning tools, you may understand, due to this powerful attack tool, it's very easy to build some similar noise that sounds very close to your voice. In that way, to bypass this security protection. So in order to protect our device and against this very representative security threats, we have several problems using multimodal assistant method. For example, the first one, using audio-visual, you can using your audio and visual signals simultaneously for using the multimodal learning. However, the problem is such kind of protection is very vulnerable to light. For example, changing positions, your facial mask, and even light condition. This kind of things is not very practical for users. So then the second solution proposed, utilize the ultrasonic assistant method. Similarly, have a problem very limited to the short distance, extremely short distance, still impractical for users. And also, this kind of things need very specific posture requirements. So in general, based on that, we propose this new mechanism, utilize millimeter wave voice multimodal identification. And a little more clarification here, millimeter wave, that is, you can consider it a very high frequency signal. The frequency range is from 24 gigahertz to the 300 gigahertz. And also it have another name, it's used for 5G network. It has very good benefits to penetrate through some obstacle and have very high sensing resolution. It's considered very emerging technology for wireless sensing area. So based on that solution, utilizing both advantages from these two sensing modalities, we hope to achieve the performance can make the system very robust and secure, especially against this motion interference, long distance limitation, and also hope to achieve noise resistant. The mechanism behind this multimodal learning is still from noise side. We know the noise is the cost-effect production of the vocal volume vibration. And at the same time, our wireless signal, millimeter wave, is also modulated by the vocal fold vibration when sensing. So if you look at these formulas, we can see no matter from the speech generation formula or our wireless sensing, millimeter wave sensing perception formula, the phase change, that is very important in both sensing modality. The phase change are very, very dependent on our vocal vibration. Here is the X, here represents the displacement. And based on that, we build this multi-modal learning for the user identification. Totally, there are 4 modules in our entire system. First one, for the initial step, signal preprocessing, is try to extract or try to do some fine-grained waveform estimation. And here, we design a cross-module waveform estimation algorithm and the construction correlation matrix as shown on the right side. This correlation matrix contains the cross-module information and by correlation demodulation, try to reconstruct the sensing signal. Second step, that is for the security purpose, for the liveness detection. And here we utilize both features, no matter from voice or the millimeter wave, to do this live detection against some malicious injection signal. In the end, we're using the correlation filters to capture the meaningful feature information in the signal and weaken the irrelevant redundant noise. Then in order to enhance the fusion between these 2 modules, these 2 will be segmented and convolved to obtain the final fusion maps. And we will feed this fusion map into a deep learning model-based recognition to achieve the user identification. We test in the real world, no matter from the general biometric performance on the large scale data set, and also test on some different conditions, like for the robustness or consistency. Specifically, we did some analysis for the security. We set up 5 different secure attacks, replay, mimicry, and adversary attack that is based on the voice modality, and also the jamming attack and the counterfeit attack for the millimeter wave sensing attack. And the performance is showing the below this area. It shows it can achieve a good performance against these attacks. So to take away message, we design a very unique, maybe novel multi-mode identification utilizing the advantage of the voice and the millimeter wave. And we, through our demonstration, through this multi-mode learning, we demonstrate the effectiveness and the robustness and the test on the different attacks and achieve good performance. That's all. Thank you. I'm happy to answer the question.
Yeah, let's take one audience question.
Yeah, for the use case of IVR, or 2 of the use cases you had in the bottom of the market, the 4 quadrants in the market size, or the market estimation, did you think about, in addition to identity, did you think about sentiment analysis? Is that part of the study in any way? Like when you're looking at like a voice assistant or the assessment of identity using voice, did you look at all at like tone and other aspects of how something is being said in addition to who said it?
Yeah, that's a good point, because for the voice user identification, that is the basic analysis performance we did in the papers. No matter the different tones, and for example, in our this one, in the real world, this test, the 100 user will see different content with their tones, and in that way, I'm not sure if I answered your question. Thank you so much.
Awesome. Let's thank all of our speakers one more time.
Okay, folks, we're going to promptly start at 4:05. I'm very excited to chair this session today on sensing. And we're going to have a lot of really amazing talks here. Just a couple of logistics. There's microphones over here, so if you have any questions, just come up to the microphone. There's going to be 8 minutes roughly of talks, and then 4 minutes for questions. And then we're going to be tight on time, so we're going to try to stick to the schedule as best as we can. Okay? Without further ado, I want to introduce this first paper titled CubeSense, Smart Environment Sensing with Interaction-Powered Corner Reflector Mechanisms. This is work by Xiaoying Yang, Jacob Sayono, and Yang Zhang from University of California, Los Angeles. Take it away.
Thank you for the introduction. Today I will be presenting our paper, CubeSense++, which explores the use of corner reflector mechanisms for a millimeter wave backscatter to enable smart environment sensing. Environment sensing, such as human activities and object status recognition, provides valuable contextual information. To sense activities, prior work has employed retroreflected tags on objects to collect vibration signals when their host objects are running, or use harmonic oscillation tagging mechanisms, which highlights the use of the object's physical movement to infer human activities. However, these approaches can only detect the presence of activities while missing fine-grained information such as the direction, speed, and angles. In CubeSense++, we expand the sensing capabilities by transforming the physical movements of objects into structured responses to millimeter wave radar using corner reflector mechanisms. Here on the right corner, the left heat map shows the signals received by the radar sensor. The bounding box highlights the location of the reflector. On the right are the radar signal changing with the rotation of the corner reflector. By decoding these signal changes, we can get fine-grained information of the activity. We use a millimeter wave radar for sensing for its potential to be integrated into smart ambient devices such as speakers and light bulbs to detect everyday human activities while preserving user privacy. I'm going to show more examples of uses of our sensing approach. Here we transform the linear motion of opening and closing the storage bin into the rotation of the corner reflector. This is an example of a user opening and closing the door of the 3D printer. We can also detect the faucet uses to monitor the water flow. The water drives the water wheel and the reflector rotates at high speed, and this can be captured by the radar sensor. Our sensing approach could also derive fine-grained information about activities such as speed. We could detect the rotation speed of the reflector to infer the speed of people walking on a treadmill. We can also detect the angle of a valve shut-off switch by observing the number of rotations made by the reflector within a specific time frame. Our work leverages a special type of reflector, that is corner reflectors for millimeter wave backscatter. This reflector can reflect instant waves back to their sources, so it can induce significantly larger reflections compared to that of objects of its size. Radar cross-section, or RCS, is a measure of reflectivity of corner reflectors. For a single corner reflector, RCS changes with the orientation angles of instant waves. Larger corner reflectors generally have larger RCS, so we can leverage this correlation to encode information using corner reflectors of different sizes. Our idea is to use their RCS to encode user activities, which are then decoded at a remote radar. Now let me walk you through the details of our reflector design. First of all, the reflector should be easy to fabricate and allow the use of readily available manufacturing techniques such as 3D printing. Second, the reflector should induce signals that can be easily distinguished from the environment, where stationary and dynamic objects constantly exist in the background, such as people walking and appliances running. These activities can all be captured by the radar, and we should eliminate their interference. So, besides employing corner reflectors that induce strong reflections, we transform object motions into high-speed rotation of corner reflectors to induce high-frequency signals. Furthermore, to detect fine-grained information of activities, the reflector mechanism should induce distinct signal patterns at different object status. This informed us to employ reflectors with different sizes arranged in a pattern. Our reflector design went through multiple iterations. First, we designed a hemisphere-shaped reflector with 4 corner reflectors of different sizes on a rotatory platform. At clockwise rotation, the signals are sawtooth waves with negative ramps. And at counterclockwise rotation, the signals have positive ramps. After multiple trials and errors in developing this reflector design, we hope to establish a consistent and systematic approach to designing the reflector. To do this, we first examined the RCS variation with the rotation of the reflector. We articulate this RCS change with angle into a math equation. In this way, we establish the correlation between RCS changes of the whole reflector and the radius of the corner reflectors arranged on the rotatory platform. Our goal is to find the optimal radius set to induce the expected signal pattern. Using this correlation, we formulate an optimization problem with certain constraints. The arrangement of the corner reflectors should stay within the platform's radius limit. We then use a linear function to fit the local peaks of the RCS to get the slope and intersection and apply the generic algorithm to solve this problem. Finally, we got the computationally designed reflector. The signal pattern of this reflector is more distinct than our prior prototypes. In terms of materials, we made reflectors out of PLA and aluminum foil, aluminum alloy, and steel. The latter 2 reflectors show much stronger reflections than the PLA one. This implies a potentially much smaller form factor for future reflector mechanisms. However, these reflectors are heavy and costly to fabricate, so we finally decided to use 3D printing and the aluminum foil for prototyping the reflector mechanisms. We developed the decoding algorithm based on first principle signal analysis. We looked into the frequency spectrum of the signals and applied thresholds to determine the existence of activities. And then we obtained the fine-grained activity information, including direction, speed, and angle, by looking into the characteristics of these peaks of the signals. We demonstrate our sensing approach with 15 everyday objects that involves translational motions, rotational motions, water, and wind flow. To evaluate our sensing approach, we deployed the radar sensor and the mechanisms in 2 indoor environments and 1 outdoor environment. Our evaluation involved experimenters performing 3 rounds of tests for each object. While people were doing daily activities such as talking, eating, walking, and exercising in the background. The activity existence and direction detection accuracy is 98% and 80% respectively. We found that encoding activities as high-frequency signals can induce a low false positive rate, but activities that involve the manipulation of metal objects, such as opening a laptop, may cause false positive. Also, the detection accuracy drops slightly as distance increases due to the lower signal-to-noise ratio. Our technique also allows the detection of concurrent activities due to the adequate spatial resolution offered by the radar sensor. Here we deploy 3 reflectors at the sliding door, grill, and faucet. On the right corner, the object turning into green color means the object is being in use. As you can see, encoding activities into high-frequency signals allowed our technique to work with the presence of user movements in the environment. Finally, I want to talk about the limitation of our sensing approach. The gear and the reflector mechanisms are bulky in our current design. However, they could be minimized with superior fabrication methods, such as metal printing. Another limitation is that we have to manually calibrate the reflectors to register their host objects to locations. This can be eliminated by employing better signal processing algorithms to identify the existence of potential reflector mechanisms. Finally, our sensing approach is limited by line-of-sight sensing. Future research could implement beamforming techniques to distinguish signals from various sources to address this issue. Thank you for listening, and I'm happy to take questions from you.
Questions from the audience?
Yeah. My name is Winston from MIT. So I have the question about how practical it is. You know, like the MM wave, it can reflect the signals from everything, humans and objects. And then also like when there are multiple the sensor you made in the same room, and how they're gonna affect the performance, and what is the distance between the antenna and the sensor, and like how many sensors do you need, like how many MM wave equipment do you need in one room, and how big is that room? So I wonder like this kind of practical problems.
Thank you for the question. How practical it is. So I think our design principle is that we want to encode activities into high frequency signals. And these signals does not commonly exist in the environments like the appliances running or people walking. They are not in very high frequency. So we want to encode these activities into like a specific frequency so that we can distinguish these signals from other appliances and from human activities. Yeah, that's for the first question. And for the second one, you are saying how far and how long can the radar sense? For the millimeter wave radar sensor we are now using is originally designed for autonomous vehicles, so it can detect a very long range, like 20 meters. And the field of view of our sensor is about 120 degrees in azimuth plane and 30 to 60 degrees in elevation, in the elevational plane. So in common indoor environment is around 5 meters to 10 meters. The distance of the radar and the object is usually within this range. So I would say millimeter wave radar sensor, we can, in common room environment, we can envision that we can just deploy one radar sensor, or we can have a better design of the antenna array so that it can detect like 360 degree. And we can locate it in a very high location so it can cover a larger range. Yeah, I hope this can answer your question.
Okay, we have time for one very brief question. And then Nathan, if you want to swap.
Hello, Marwa from MIT CSAIL. Very cool work. I really appreciate you like looking and tapping into sensing. I had two very quick questions. The first one is like, you know, in terms of size, it does seem that for some of the applications that have like a smaller footprint, it did seem like a bit bulky. So I was wondering like if you were going to miniaturize it, like how small can you go? And then the second question that I had is, if you wanted it to be like more discrete, have you thought of ways to kind of like have the sensor be like more hidden from other people's view? Yeah, these are two of the questions.
Thank you for the question. And how small it can go, I would say we haven't tested how small it can go, but we do test some metallic material, and the reflection is much more stronger than our current very thin aluminum foil. Is around 4 times much strong. The reflection is about 4 times much stronger. So I would say our current sensor is around 10 centimeters diameters, and it can be much smaller. And for the second question, yeah, we hope to we hope our reflector can hitchhike existence of mechanical structure of our objects, like the door, the hinge, or the track of the sliding door. So we can hide this reflector within these mechanisms, so that it's not that intrusive to the environment. Thank you.
Let's thank our speaker one more time. Our next paper is Smart Poser, arm pose estimation with a smartphone and smartwatch using UWB and IMU data, presented by Nathan DeVrio from Carnegie Mellon University, along with Vimal Mullian and Chris Harrison.
Thanks, Gerard. Hi, my name is Nathan DeVrio, and today I'll be presenting Smart Poser, a work I completed with my co-authors Vimal Mullian and Chris Harrison on estimating pose with a smartphone and smartwatch using ultra-wideband, or UWB, and IMU data. Yesterday we showed off a demo, which I hope many of you got to try. So the ability to track a user's arm pose can be useful in a wide variety of interaction contexts, ranging from tracking form in sports to physical rehabilitation, context-aware assistance, and occupational safety. Many people already wear smartwatches. However, these devices often know more about their users' legs, lungs, and heart than they do about the arm that they're worn on. Identifying the mentioned applications and acknowledging this gap are what motivated us to create our system, Smart Poser. So Smart Poser is a software-only system that uses UWB and IMU data from a smartphone and smartwatch, devices that many people already own, to track a user's 3D arm pose. So our goal is that users can wear and use their devices in the same way they're already used to, put their phone in their pocket and wear their watch on their wrist, and we could enable an entirely new interactive feature, arm tracking, with just a software update. So when identifying ways to improve wearable pose tracking, we noticed that in prior work, orientation data from worn IMUs has been the best way to track pose with a wearable approach. Recently, many smart devices have begun integrating UWB into them for nearby localization. Past research in non-wearable setups has also shown promise for tracking pose with UWB beacons wirelessly. Thus, we hypothesize supplementing IMU data with inter-device distance measurements obtained by time of flight from UWB may improve performance through a fusion approach. So here you can get a glimpse of how well our system's tracking works. As mentioned, we take the distance derived from UWB between a phone and watch as our core feature, and then supplement it with data on the orientation between the two devices obtained from their IMUs. So here in the middle you can see our features, and on the far right is the 3D joint key points of the arm that we predict. So under the hood, our system is taking raw UWB data and passing it into an LSTM that corrects errors in distance ranging. The corrected UWB data is then passed alongside the relative orientation between the two devices into a second LSTM that estimates the 3D joint key points for the elbow and wrist. The fact that we only use relative orientation is important because it enables the system to continue working even when the user moves their body around. Our model is also lightweight and has been tested and run on an iPhone with less than 1 millisecond per inference. So to supply the data to our model, we created apps that use on the devices that use Apple's Nearby Interaction API to acquire distance with UWB. So this is a special API that's made to work with the U1 chip found in Apple devices. However, it can also work with custom hardware and third-party devices, which is actually something we tested in the early stages of the project. So a key challenge with this particular UWB implementation, and a lot of UWB, is that it requires initiating and maintaining a session to continue reporting distance data. This session can sometimes abruptly end for different reasons, such as devices going out of range, or even things like body occlusion or erroneous data. So in our system, we created a state monitoring loop that can restart the session if it ever ended. However, this is one of the challenges of using UWB. Another challenge was on the iPhone, UWB is actually optimized for a fixed field of view cone out of the back of the phone due to the internal tenet design. So when in the pocket, we actually notice interesting behaviors that when you have poses within that field of view cone, you can obtain higher fidelity data and even 3D angles of arrival in addition to just distance. So we initially tried taking advantage of this better data when available, however, ultimately found that the field of view of poses was too narrow to make practical use of it. Not to mention, users sometimes put their phone in a different orientation or backwards in their pocket, so you might not be able to use this. In the future, a better antenna design may unlock more of this capability. So one way we were able to markedly improve our UWB data was by passing it through a correction module trained on ground truth data from Kinect. So as you can see in this graph, for some poses, like putting the arm far above the head, there's greater occlusion or distance from the pocket, and the error in the raw data shown in blue drastically increases. However, by correcting for the data for such poses, which you can see in orange, we were able to drastically reduce the average error by as great as 85%. So to evaluate Smart Poser, we conducted a two-part user study where we had 10 participants perform a series of 20 terminal arm poses in a random order, and then repeated this process for a total of 10 rounds. This procedure was then run again on different daily activities instead of gross arm motions. Importantly, we continuously collected data as participants moved between different terminal poses in the study. So for example, if I was presented this pose and this pose, we would continuously collect data as participants move on their own between the two. Thus, with the random ordering of 20 poses, there are actually 190 possible pairwise transitions we captured throughout each study part, not just single static poses. So here's a clip showing arm tracking performance when performing some of those different daily activities that we captured in our study. So you can see that instead of just standing still, users were actually moving their body around to perform different tasks like vacuuming and incorporating organic arm movements. As mentioned before, we predicted the 3D joint positions for the elbow and wrist and found that in the best case, which occurred when training on combined data from both parts of the study, our median error was 11 centimeters for the elbow and wrist combined and 13.3 for just the wrist. Compared to prior work, this performance is significantly better than wrist tracking from Mullen et al.'s IMU poser and marginally better than Shen et al.'s arm track, and we also enable new features such as the ability to operate on the go without recalibration. Looking at the benefit of UWB correction during the study, we also saw that correcting UWB improved correlation with ground truth connect data, and the error improvement was over 10 centimeters greater for the gross motion part of the study, where users performed more dynamic arm poses with greater occlusion and separation between the devices. So if we visualize that spatial error of the wrist joint positions, you can see some of these tough spots. So wrist positions that put the wrist far away above the head, so it's farther from the pocket, or even behind the back of the phone, there's greater error because the line of sight between the two devices is no longer good. Finally, we also performed an ablation analysis on our study results to quantify the benefit of adding UWB data over purely IMU. This analysis showed that adding UWB data drops the median error by 3 centimeters for the elbow and 3.4 for the wrist, roughly a quarter improvement. Considering how past models have differed in performance by fractions of a centimeter, we believe this validates the benefit of UWB. So for the last part of the presentation, I want to quickly show some demo use cases where we envision Smart Poser could be used in the future. One is for physical rehabilitation. So after a rotator cuff injury, a background process could run on a user's watch that tracks each stage total arm movement, duration lifted, maximum extension, and elevation reached. More interactively, a smartwatch app could guide people through a Tai Chi routine, automatically advancing next instructions once recognized, as well as providing feedback on performance during the routine. Arms are also involved in many physical exercises, thus tracking the arms could be used for fitness-oriented applications. Finally, a worker's watch could vibrate to help prevent injury by alerting them when they lift boxes above their head away from a safe range. Thank you. This concludes my presentation, and I'll now take any audience questions.
We have time. Go ahead.
Hi, Nikita Joshi from the University of Waterloo. This looks really cool, and I'm really excited for future use cases. I guess I'm just wondering, how dependent is it on the phone being in the pocket? Because a lot of time, women's clothing, unfortunately, pockets are too small for your phone to actually fit in your pocket. So I'm just wondering if you had thought about that and how well it works with not having the phone in the pocket.
Yeah, thank you for the excellent question. This is actually something we did think about. We didn't, within the scope of the project, explore a lot of these different use cases, but we do talk about it in the paper. What the system relies upon right now is having a static position of that phone because the arm is moving around, so you need the phone to stay static. So obviously, in different pockets, it would still work the same. We hypothesized that if you had something like a handbag that it was roughly in the same position, you could still track the phone there. You bring up a great point that a lot of people don't have pockets in their clothing. So a future area that this could be improved is Apple, for example, now has UWB in a lot of their headphones as well. So you could have a device worn somewhere else on the body, also static, that could fulfill the same role as the phone.
Thank you.
Hi, AJ Hashi from Meta, and I actually have two questions. One is do we assume that system actually knows the position of the phone relative to the body? And then the second question is, UWB also support angle of arrival, and if I understand it correctly, you actually use the distance, not the angle. But have you tried it? And then if you have tried or you have thought about it, how do you think it's affect the performance of the system?
Yeah, could you repeat the first part of the question?
Yeah. Does the system knows where the phone is in terms of body, like left pocket, right pocket, like somewhere in the body? Does the system knows that as a prior knowledge, or it's automatically calibrated to estimate?
So to answer your first part of the question, yes, like the phone position, that's assumed as a prior of the system, because as I mentioned in the previous question, you need to know that to know the arm position.
Totally depends on where the phone.
Yeah, and then as far as the second part of your question, distance is the only new metric we're getting from UWB. So I think incorporating other things like phase or angle would be something left for future work.
Okay, I see. Okay, thank you.
Thanks.
We have 90 seconds for 2 questions, if you can make it.
Yeah. Hi, really nice presentation. I was curious if you could talk about, do you have to hard code in the height and how that would change? Because the height from someone like me is much different than the height from someone else who has in their pocket and is raising their hand.
Yeah, thanks for the awesome question. So this is something that's sort of like a hard-coded thing into the system. So we were actually doing this last night at the demo session if you stopped by, but we sort of see this as a way that, like, right now when you buy a new iPhone and you're using Face ID, you have to do a calibration to set up Face ID first. So we imagine something where you could either manually put in, it's really arm length, that's the measurement of the body that we need. So you could either manually put that in, or you could use UWB to measure that distance. And once it's set once, you know, people's arm lengths don't really change, and so it could work indefinitely for the future.
Thank you.
All right, 30 seconds.
Lucius Schillenball from Waterloo. You mentioned it runs with low latency on an iPhone. Do you also have insight like how much of the computation power of the iPhone that requires and whether that drains the energy, the battery?
That's a good question. I don't know off the top of my head how much computation it requires on the iPhone. I do know that it runs pretty well, but we could chat offline to maybe figure out that more.
Let's give our speaker one more round of applause. Our next paper is titled Pressure Pick, Muscle Tension Estimation for Guitar Players Using Unobtrusive Pressure Sensing. This is work presented by Andreas and the team at ETH Zurich. By the way, if you have not seen the YouTube video of this talk, I highly encourage you to do so because the background music is very nice. Also played by our author over here. All right, take it away.
For the great opener. All right, hi everyone. Today I would like to present Pressure Pick. So my name is Andreas Fender, and this work was done together with Derek Witzig, Max Möbus, and Christian Holtz. Oh, sorry for that. Okay, that looks better. All right, so the goal of Pressure Pick is to unobtrusively measure whether you have high muscle tension while practicing with the guitar. So the way this works is that there's a small pressure sensor attached to an ordinary guitar pick, and then while you're practicing with the guitar, the device measures the pressure, transmits it to the software, and then later on, after practicing, you can, for the song that you practiced, assess whether or not you were very tense in certain parts. You can inspect every part and see how tense you were while you were practicing with the song. So before I get into more detail, I want to step a little bit back and talk a bit about the motivation for why this is even needed. And one key thing here is that when practicing with the guitar, it's not only about the sound, it's not only about it sounding good, but it's also about the correct execution, which can be very subtle and which can be sometimes also not audible. And in particular, what we're particularly interested in here is the execution in terms of exerted pressure. And applying too much pressure to the pick can lead to muscle tension, which in turn then can lead to a very quick fatigue, so you can maybe not practice as long, constrained movements and limited flexibility in terms of biomechanics, limited artistic expression. If you always practice in the wrong way, then your artistic expression in the long run might be limited, and also it can even lead to injuries, short-term and long-term. of course, there are different ways this has been handled conventionally. Like most prominently, guitar teachers kind of have an eye for like pointing this out and then telling the student to like maybe slow down a bit or relax the muscles. But of course, when you're between guitar lessons or also when you're teaching yourself, then the student needs to kind of assess themselves whether the muscles are tense or not. And then of course there have been also efforts to automatically measure muscle tension between guitar lessons or also when being self-taught. And so I want to quickly talk about some existing approaches, and of course the most direct way of like measuring muscle tension is to use EMG. And of course there are like many medical grade devices which can fairly accurately measure the tension in the muscles. But of course, so the good thing here is that there's like works from many years ago already which show that this can actually have a really positive impact on instrument learning when you are having an accurate device to actually like kind of conditions you to keep your muscles relaxed, and that can have a positive impact on the training outcome. But of course, this is very obtrusive. So what then people tried also in HCI is to use less obtrusive setups, as for instance with the EM guitar by Carlos et al., where they use lower cost and less obtrusive EMGs. And another approach is to equip the instrument themselves, as for instance with Let's Frets by Markey et al. But then of course the problem is if you have like 10 guitars at home, you don't want any specialized sensing on the guitar itself, like you want to just practice with whatever guitar. So and then the overall goal with all of this is to enable unobtrusive practice and unobtrusive ways of practicing with low muscle tension without equipping the instrument. And this is where pressure pick comes in. So, and as I showed in the beginning, so here's a quick like kind of setup. So we have a simple FSR force sensing resistor on the guitar pick, and then you practice the song, and in the end you get automated feedback. And of course, for this to work, we need to understand pressure patterns and then how they relate to muscle tension. And for that, we conducted a data collection, which I want to very briefly run through, at least through parts of it. So our apparatus looked like the following. So we used 3 force sensing resistors, one of them on the guitar, like a long FSR strip, and then 2 sensors on the guitar pick. And in the end, we wanted to find out which of those sensors work best for the final device that we want to build. And then the guitarists, 12 in total, had to conduct different exercises. So starting very simple, they just had to hit the same string over and over at a fixed speed. And which is then called down picking, if you hit the string from the same side. And then very similar sounding is alternate picking, where you hit the string from both sides in an alternating motion. And this one was for single strings, but then we also wanted to see what do the pressure patterns look like for multiple strings, like when you play so-called power chords, which means that you hit 3 strings at once. And then we also had them play different sequences of power chords, so playing 3 strings. And then accordingly also open chords or bar chords, so both of them, to then also play with 4 or 5 strings at once. And, And then they had to play this in 3 different speeds, so it's starting with 120 beats per minute, going to 150, and then also 180, and then 20 seconds for each. And then the whole sequence we started with 120, and then we did that for all the 12 exercises. And so I won't have time to go into detail on like what the patterns actually look like. So here are just like 2 of the plots, but I want to quickly zoom in and at least give a little bit of an idea like of what those patterns look like. And what we can see here is that for quarter notes, we can pretty clearly see when, like the moments when the pick hits the string. And then for faster notes, of course, accordingly and with an increased frequency. And then interestingly, for alternate picking, you kind of see that it's like the pressure patterns kind of like have half the frequency of the actual notes being hit. And using that information, like first kind of like qualitatively understanding those pressure patterns and then also trying to identify features which are then best for predicting the muscle tension. And one thing I forgot to mention, I'm very sorry, I have to go back for a moment, is that for each of the sequences, the guitarists were rating like the muscle tension they had in that particular sequence, which you can then also see like in the plots here where they gave a rating for each of the sections, and then the goal was to get from the plot from the pressure patterns to the subjective ratings. And then that's what we did with the feature extraction, where we then found out that just taking the absolute pressure is not enough to estimate the muscle tension, because there were very many individual differences with like how much pressure they applied, and also depending on the technique and different factors, the absolute pressure exerted was not really a good indicator, but instead we looked at things like the variation, like standard variation, for instance, which were much better indicators. And then we also found that on the front and on the back of the pick, the results were almost the same. And then also on the FSR strip on the guitar neck provided comparatively little information. And then therefore, based on this, we built then the final prototype, which I'm very quickly going to run through because we've already seen it a couple of times. So just very briefly about the hardware. So it's a variable device where the pressure pick sits here on the pick, and then is being streamed wirelessly to the computer. So very simple device. Of course, if you want to know more about the hardware, you can read the paper. And because I'm a little bit out of time, I'm going to fast forward a little bit in this part and showcasing the interface with this one here. I hope I'm not sure it's audible. So here we can see like one example song, which is actually using alternate picking, which means like only every second hit is basically recorded in the pressure pattern. And then the same also when, it's maybe not super easy to see when you're not playing the guitar yourself, but there are different like techniques involved in here, like ranging from hitting single strings, multiple strings. And then what we can see here very briefly is that, for instance, here in the chorus, we see that there's like those notes being hit here, but the frequency is kind of like half of this. And then using this information, we can then use this to estimate the pressure pattern. But again, for our prediction model and everything, I have to refer to the paper. And to very quickly conclude, so we suggest an approach for unobtrusively estimating the muscle tension during guitar practice with a data collection with 12 guitarists with varying experience. We did a data analysis to identify the best features for muscle tension prediction. And in the end, we then also built the variable pressure pick device and front end, which was informed by that analysis. And with that, I'd like to thank you and then, of course, open for questions.
Now we have time for a few questions. I can ask the first one. Was that Nirvana, Weezer, and Papa Roach?
Nirvana, yes. The second one was?
I thought it was Weezer, but never mind. First question.
But the third one was correct.
Thanks.
Papa Roach was correct.
Hey, I'm Richard from the University of Washington. This is super cool. I was wondering if you had any thoughts about running this in real time potentially, and if you think real time feedback could be helpful at all, or do you think like this post hoc kind of analysis is more useful?
Yeah, that's a super great question. So of course, like during the project, we were also like often thinking about like what would this look like in real time, and but of course before we get there, there are a lot of like other problems to solve, because what we wanted to find out here is sort of like what are the differences between the different playing techniques, and if you want to enable real time, you also have to know which technique is employed in this very moment. Like, are you playing a chord, are you playing single notes, and so on. So you would first need to detect what technique you're employing, and then based on that, you can then give real-time feedback. So, and then, but by first, like in this work, we did it in a way that the song was known, so we would know what note to expect, and then like just use whatever predictor was best for that particular technique, which would be then used in that part of the song. And so it's a very natural and really nice next step to then go real time and say, okay, we have to inject this step in between to first find the technique and then do the prediction based on that. Yeah. It's
awesome.
a very great
Thank
question.
you.
Thank you.
All right, 30 seconds for one final question.
Hi, Bala from Microsoft Research. How do you calibrate for the user, right? Because someone might hold a pick very hard, and that might be their normal, and someone might not. So.
Yeah, this was actually, so also a really great question, and also something we looked at for a really long while, because we were surprised how different the differences actually were. Unfortunately, I don't have the plot at hand, but like there were people who almost applied no pressure at all, like almost none, and then others who were like really pressing it hard, but really didn't feel that they exerted a lot of muscle tension. So in the end, it's maybe like another future step to also look into like per user calibration. But what we found is that or like what we can say at least is that because of that individual difference is that we cannot use absolute pressure as an indicator, and we have to look into like other features if we want to enable across users, right? In the future, we can of course also look into, so if we know the base pressure that a certain user exerts, what other features are then maybe better? So that's then also like a different, also interesting question if we allow per user calibration.
Yeah, thanks a lot, Andreas, and also I loved the music in the presentation.
Thank you.
Thank our presenter one more time. Our next paper is SUPREYES, S-U-P-R-E-Y-E-S, Super Resolution for Eyes Using Implicit Neural Representation Learning. This work is going to be presented by Chuhan Zhao from the University of Stuttgart.
Thanks. Today I'm going to introduce our work, SUPREYES, Super Resolution for Eyes Using Implicit Neural Representation Learning. The work was done together with my colleague, Zhiming, Mihai, and Andreas. So how many of you are familiar with eye trackers? Quite many. So basically nowadays there are different types of commercial eye trackers. Mobile eye trackers, including wearable eye trackers and portable eye trackers. Due to the limited design space, the sampling frequency of mobile eye trackers is up to 200 Hz. However, stationary eye trackers are able to track human eyes at several thousand Hz. Recent studies in eye tracking research demonstrate that high-frequency gaze data is the key to the success of many applications, such as eye movement detection or user authentication. One naive way to increase the sampling frequency of mobile eye tracker is always updating your hardware. But it's expensive and need time to learn how to use it. So is there any way to increase the sampling frequencies of low-resolution gaze data without updating the hardware? We propose SUPREYES, the first software solution for gaze data super resolution. SUPREYES learns continuous gaze representation from low-resolution gaze data to upsample the gaze data to arbitrary resolutions. We showed that SUPREYES significantly outperforms commonly used interpolation baselines in arbitrary scale gaze data super resolutions. And using gaze-based user identification as an example, we demonstrate that SUPREYES can benefit gaze-based downstream tasks. Things like those traditional interpolation methods can upsample the data to any target resolution. So we hope our method can do the same thing. Implicit neural representations have shown a great success in learning continuous representations, for example, in 3D reconstructions, and also in arbitrary scale image super resolutions. Here is an overview of our method. So the method is trained in a completely self-supervised fashion. So our low-resolution gaze input is downsampled from high-frequency ground truth data. And then a feature extractor extracts global features of the input low-resolution gaze data. Then given a query time coordinate, we extract the local features around the coordinate to predict the gaze location. So different from prior works in image domain, which heavily rely on the pre-trained feature extractor. Since there is no such thing for gaze data, so we not only train our model with the loss for the final output, but we also add another loss function for our feature extractor to obtain more robust features. Our model is trained and evaluated on the gaze-based dataset, which is a large-scale dataset with 1,000 Hz gaze data. it can provide us the high-frequency ground truth. And we trained like 3 different models on this data set. We picked 3 popular sampling frequencies of mobile eye trackers as the input frequencies. And because previous work suggests that 250 hertz gaze data or higher gaze data is better for biometric purposes, so we picked these target frequencies in training. So we compared our method with commonly used interpolation baselines. Linear, quadratic, p-chip, and cubic spline interpolations are arbitrary scale gaze super resolution. The results of other interpolation methods can be found in our paper. We evaluate the performance use 3 time series matrix. So mean absolute error, mean square error, and dynamic time warping. So in general, surprise achieves higher similarity to human gaze than all interpolation baselines from a time series perspective. However, time series matrix alone may not be sufficient for the evaluation, because we also want to know whether the model can generate gaze samples that are in line with user-specific characteristics during the upsampling process. Therefore, we merged the validation and test recordings in previous experiments as a dataset and perform a gaze-based user identification task across all 130 users. Our assumption is that after the upsampling, if the performance of on the high-resolution test set is better than the performance on the original low-frequency data set, so the upsampling method generates meaningful user-specific gaze data. We use a CNN model for the user identification. So the learnable parameters are all the same for different input frequencies. So we can tell the performance changed only because of the upsampling. So we upsample 50 hertz gaze to 100 hertz and 200 hertz, and also upsample the 100 hertz data to 200 hertz with surprise and other 4 interpolation baselines. And we use equal error rate EER and the classification accuracy to evaluate the performance. So here are the results. So all the improvements are underlined. So we can see all the baselines lead to a performance drop in the matrix. And for upsampling scale 2, single stage surprise leads to improvements in both evaluation matrix compared to original 50 hertz and 100 hertz results. And notably, the results of upsampling 100 hertz to 200 hertz rival those of the original 200 eye tracking data. When the upsampling scale goes higher to 4, the task becomes more challenging. So the multi-stage surprise slightly improves the results, but still falls far short of the performance achieved on the original high-frequency data. So to conclude, surprise is the first software solution for gaze data super resolution, and it can generate user-specific gaze samples in the upsampling process. In addition, it can be used in several applications, for example, enhancing the low-frequency eye trackers, augmenting eye tracking datasets, or improving the performance of gaze-based downstream tasks. So for more details, please check our project website through the QR code or contact me directly. Our model will be available on this website. Thank you for listening. I'm happy to take any questions.
We have time for several questions, yes.
Hi, I'm Taejun Kim from KAIST, and I do gaze stuff for my PhD work. And then I might not fully understand this work, but like, is that real time? For example, when I'm using a gaze collected data for real time to real time interact with the environment in AR, VR, or real world IoT, like the up sampling should be made real time to be used, right? So I was like, yeah.
Yeah, so for our model is not real time, so it's a kind of it's a limitation of this work. So every time we take 1 second gaze data as input. So I would say it can still be used in several applications. For example, if you already have a 50 Hertz data set and you want to increase the data set to merge maybe with your new, the data collected with your new devices, then maybe it can be used in this case. Or so now our method basically is a post-processing method for gaze data.
Yeah, and then like it might be a future work, but I was like wondering if like the saccade velocities or like blink rates can be like different for some, in a cognitive, like different cognitive domains.
We discussed this in our paper.
Oh,
so,
yeah.
Yeah, we plan to evaluate also on eye event level. So every eye event like saccade, smooth pursuit, can modeling the real human eye behaviors on this event level.
Thank you very much.
Thanks.
Next question.
Hi, Andrew from INSPIR Brazil. Very interesting work. So pushing this to the limit, how do you think it would work with, for example, camera-based eye trackers that have a lot less accuracy for the spatial resolution? So would it still, I think the question is, how does it handle noise in the gaze estimation?
Yeah, like noise always came with the eye trackers, right? So like no matter what kind of eye trackers, you always have some noise. Even for the stationary eye trackers, just the noise is like less than the mobile one. So I would say like if you are in a well-controlled data collection setting and your calibration for the user is like correct and you sometimes always recalibrate it, then maybe the data collected with your mobile eye trackers is almost the same as the data you downsampled from stationary 1000 Hertz eye trackers. I would say it really depends on the experimental settings. So if you are in a really extreme experimental settings, I would assume our method won't work. So
yeah, makes sense. Thank you.
Thanks.
I have one question. In the model that you trained, will it work only for a particular type of eye tracker, or will it generalize to other eye trackers?
Yeah, it's a generalizable model, since like the input we take is not the coordinates on the screen, so it's a 3D vector. So basically we convert it to degree of visual angles. So for every eye trackers, you can convert your collected data to the 3D vector and represent as a visual angle. So we can take the gaze data from like any kinds of input.
Okay, great, thank you. Let's thank our speaker one more time. Our next paper is titled Joie, a joy-based BCI. This work is presented by Angela Vujic, Shreyas Nisal, and Patty Mays from MIT Media Lab.
Thank you. I'm going to be talking about a slightly different kind of sensory sorcery. My name is Angela Vujic. I'm a PhD candidate in the Fluid Interfaces group at the MIT Media Lab, and today I am presenting Joie, a joy-based brain-computer interface. So in recent years, EEG devices have been getting smaller and available in everyday form factors. This means that we could introduce brain-computer interfacing to everyday, non-expert users in everyday environments, such as a student using their mental workload to adjust reading materials for an exam. In HCI, BCIs have been studied for augmenting personalized learning, meditation, and attention. But what about emotion regulation? We don't often talk about effective computing at UIST, but it would be really interesting to think about how integrating emotion regulation into interfaces can passively or actively influence well-being. This is especially important because as of August 2022, about 32% of US adults reported symptoms of anxiety or depression. But historically, detecting emotion from brain sensing has required significant data collection, complex modeling, and bulky equipment, which particularly in 2015 at UIST, Aranya et al. Presented an anger-based BCI using FNIRS, which was with 2 sensors on the forehead, but required significant bulky desktop equipment. With Joao, we're proposing an emotion-based BCI that can use few electrodes, minimal training, and wearable devices. The way we do this is by recording EEG from the prefrontal areas, and after doing denoising, we look at something called the alpha frequency band. What's super fascinating is that joyful imagery can actually activate a relative alpha asymmetry that you can pick up using just simple mathematics and no machine learning. And then what we've done is we've mapped this asymmetry to a one-dimensional control in a video game in an infinite runner format. So to give you a background to understand how this works, we have to think about how the brain is functionally organized. The prefrontal cortex is the executive functioning center of the brain. It's important for task switching, memory updating, and response inhibition, which includes emotion regulation. And one model that we can use to understand this activity is actually a behavioral one called motivational direction. Left prefrontal activity, relatively, is associated with an organism's motivation to go towards something, while right prefrontal activity is associated with a motivation to go away from something. These motivations are then coupled with emotions. So happiness and anger, so it's not specifically valenced, can cause approach. And then fear and depression can cause withdrawal. The other really important thing about this brain activity is that it's time-locked to a stimulus. So let's say you have a cookie, and whether or not this causes approach or withdrawal in you, whether you're on a diet or not, this will then have a brain response that occurs with that stimulus, which is important when using it in a real-time system, because then you know that that signal is going to occur in a pretty defined period. So the goal of JWA is to help people increase activity in this relative left prefrontal area. We designed this as an infinite runner game in a pretty friendly, joyful format. We designed the game with something called operant conditioning, which is a classic psychological technique to reinforce different kinds of behavior. The coins on the left are meant to reinforce relative left brain activity, and they are hence tied to significantly greater signal in that area. And then on the right side, we have negative reinforcement for the opposite activity. And of course, in the middle, there's no reinforcement. So in our first evaluation, we decided to use a wet electrode system, the Neuroelectrics Anobio 32. We recorded only 8 electrodes from the left and right frontal areas, and we did essential EEG signal preprocessing, feature extraction, and classification, so like the bandpass filters, detrending, et cetera. And then for classifying our data, we were simply using the difference in alpha power between the 2 frontal areas. And we recorded a baseline of this difference before starting the game, and created thresholds where if you're able to increase your activity by 0.85 standard deviations in either direction, this is then mapped to the neurofeedback in the game. So for example, the right side is what I mentioned the car was, the middle had no feedback, and then the left was tied to a positive reward. In our first evaluation, we wanted to see whether or not joyful imagery leads to an increase in relative left brain activity. And this was to determine if the motivational model can be used to create a joy-based BCI. We ran a 2-week placebo-controlled study. We had 20 participants complete 5 game sessions over 2 weeks for a total of around 120 lab hours. And participants practiced joyful imagery for around 24 minutes per session, 8 minutes at a time, 3 times per game. So this included things like traveling, friends and family, achieving awards, pets, etc. Our primary hypothesis had to do with trainability. We hypothesized that participants with instructions to imagine positive approach-motivated content would perform significantly in the game, significantly better in the game over multiple sessions. We had an experiment group that imagined joyful imagery with real neurofeedback, and a placebo group that imagined joyful imagery with fake neurofeedback, and a control group that was told to discover the strategy and also receive real neurofeedback like the experiment group. We found in our 2-week placebo-controlled trial that the experiment group significantly improved in their ability to activate our target brain region, which is very exciting. Specifically, in our regression, we used a linear mixed effects model controlling for random effects, which demonstrated that only the experiment group had a significant increase at a group level in relative left activation with repeated game sessions as the predictive variable. And when we look at the mental strategies people reported using, they were indeed pretty joyful, with travel being the most popular strategy in the experiment group and happy memories being the most popular strategy in the placebo group. And also what's very exciting is we ran 1-week follow-up interviews over Zoom after the experiment, and we found that people reported using their mental strategies outside the game without us asking them to. So this is actually how we want people to use the system. For example, we had one participant who used their imagery during sailing to reduce their fear of tipping over. So the idea is that if you have this environment where you can practice invoking emotions on command or doing emotion regulation with mental imagery, let's say if you have social anxiety, it stresses you out to go to conferences like UIST, you use your mental strategy to regulate your brain activity before you're presented with a stimulus, and then that helps you create more approach motivation, which has been shown to help with anxiety and depression generally. So in future work, because we ran our first evaluation with EEG CAP, we're really interested in how these kinds of systems can be made using smaller, more wearable devices and integrated into VR headsets, eyeglasses, etc. Just like at the beginning when I was talking about how the size and cost of EEG headsets has been steadily decreasing in recent times. Thank you so much. I'm happy to take any questions, and here's my contact info. Do not hesitate to email me or follow me on social media.
We have time for several questions. Yep.
Yurai Tanaka from University of Chicago. Is there any alternative game design that could potentially preserve also the user's sense of agency of their thought? So imagine if you actually deploy this system, if you know that you're going to use this system that steer your thoughts to positive things, if the user actually knows that, they feel like their thoughts being like kind of like redirected or sometimes manipulated by the system, so they will actually have some like suspects to the system, or like I guess I think there's a challenge on that for the design of the interaction. So if I use your device, let's say, and then in order to win the game, collect more coins, I need to keep thinking about positive things, right? And then I know the purpose of the system, I feel like I'm manipulated by the system on my thoughts. Is there a solution for that? Or like, I think there is a design.
Are you saying that the UI interferes with the task? And like, what is an alternative game design to maybe enhance the learnability?
Yeah.
Oh, interesting. That's a really good question. I think that in general, it is really hard for people to do mental imagery. It's a very, like, we did like a NASA TLX and everybody reported, like, extremely high effort, cognitive effort. So that's just a general rule. I think any system that can teach people how to do it better and maybe quantify it so that the strategy selection becomes easier is good. There are, like, based on the way that we designed the system, There are a number of feedback modalities that could be used. We had a number of users report that they would prefer a non-visual modality so that they could potentially close their eyes and then subsequently have like haptic or audio feedback that's associated with the task. I also think there is some ways to integrate this with passive brain-computer interfacing, as opposed to having an active neurofeedback task. You could make this a part of a system where the system is dynamically adjusting itself to the user's thoughts, and actually they may not be aware of that, though I'm not sure how effective that would be for the strategy selection, because I think the idea of this is that you learn a strategy in the game that you use in real life later. We have found that when we run a few hundred sessions with 3 different devices with the system, and what we found is that people who are performers, like actors and musicians, very interestingly tend to do better in the task and report greater enjoyment. So it's possible that maybe even we need to learn from our users themselves on how to better design the game, or maybe even provide more instructions on what to imagine. Yeah.
Great answer.
We have time for one very, very quick question. If you do it really fast, we could do 2. Super fast.
Thank you for the great talk from Stanford University. I was curious, in your experiment, you mentioned a 85% of the standard deviation threshold for determining decisions. How did you decide on that? Or is that a parameter that needs to be calibrated for every person?
That's a really good question. I do think it should be calibrated in the future. It came from cognitive science literature, so the asymmetry index that we're using has been really well studied in a lot of different, in cognitive science and neuroscience respectively. And for what we were doing, the theoretical accuracy is supposed to be around 80%, which is really, really good for an emotion-based BCI that uses no machine learning, nothing, just like band power analysis with a few electrodes. So that's why we stuck with what was already reported in the literature. But I think a good future question is to think about how to optimize that based on the game performance, especially because some users reported blaming themselves when they didn't do well, and you don't want to demotivate people in this kind of environment that's supposed to be helpful and improve emotion regulation.
Thank you. Let's thank our speaker one more time. Our last talk of the session is titled, I might butcher this title. What is it? Pantuena. Okay, Pantuena. Mouth pose estimation for AR/VR headsets using low-profile antenna and impedance characteristic sensing. This work is presented by Daewoo Kim, and along with the work at Carnegie Mellon with Chris Harrison.
Hi everyone, I'm Daewoo. Let me adjust this microphone a little bit. Hi everyone, I'm Daewoo, and I'm second-year PhD student at Carnegie Mellon. I'm happy to share our work as a last presenter today. Our project is Pantuena, and this work with my advisor, Chris Harrison. We envision full-body pose reconstruction in metaverse for better immersion in virtual reality. Mouse pose sensing is particularly important. A large body of literature says if facial expressions matches to situational content and spoken contents, it can increase trust and clarity among users. As most this is important problem area, there has been several work reconstructing mouse pose in VR. The most popular method is mounting camera in front of the user's face or wide-angle camera in the headset. But these optical methods still raise privacy issues, capturing close-up body parts as well as background image. Next popular method is using audio from people's speech. Specific sounds such as oo or ah generally form a certain mouth poses, and it can be utilized. But this method is not generalizable to silent speech detection, silent facial expression. And here's a video. It's a clear example. I'm smiling, but virtual avatar could not track silent facial expression. Last, in biosensing method, sensor in the headset injects signals into the skin, but it requires the sensor consistently touching the skin to work and often require calibration each time whenever system is worn. Pan2NR does not require any images or audio, neither require direct contact, yet it is low profile that is suitable for headset form factor. Okay, then now let's see how does this work. Here's an antenna, and it radiates the electromagnetic wave. As human tissue is conductive in RF signals, human face is electromagnetically coupled to the antenna and affect the signals. When the signal meets the face, partial signals is reflected back because of the impedance discontinuity between antenna and the face. The reflected signal could be observed with different magnitude. Also, the reflected signal's phase can vary. Now we have 2 data points. We can further sweep the frequencies of injected signals and see the frequency response. Any phase deformation, such as opening mouth, affect the antenna's signal. We can introduce one more antenna to capture the transmitted signal. Then we finally get 4 signal lines for better sensing. So let's look at the signal from our prototype. It would be better to see actual signal from the live demo. So I prepared live demo, but it requires the internet connection. Hopefully, this internet connection is working well. Let me first connect the headset to the computer.
I can't see anything. You'll have to figure this out.
I see. Display. Okay. Let me open the our signal visualizer. And whenever I'm talking, you can see the signal is changes. And let me show you some clear example. If I close my mouth and open my mouth, there's very consistent changes in signal. And now I'm gonna open my demo. And here's the avatar. And whenever I'm talking, you can see the mouse poses also changes in the avatar. And let me try to smile. And you can also do different type of smile. Smile teeth, and smile open, and mouth open, and puff cheek. All right, it was my live demo. So yeah, as you can see, we support 2 types of application. And my advisor, Chris, is wearing the headset. And okay, then how could we get here? How to make such kind of system? We had several antenna design iterations for performance optimization. This antenna design process was boosted with electromagnetic field computer simulation. Because of time limitation, I will briefly summarize the main findings. For more details, please refer to our paper. In the first design, the slot antenna topology was selected. Slot antenna has a couple of advantages. It is low profile, and it has a directional radiation pattern, potentially reduce the noise pickup from the environment and hand gestures. We also explored the opportunity to have secondary antenna. The main finding in this exploration is polarization matters. If 2 antennas have different polarization, the interaction between 2 antennas are less. Rather, a better coupling effect is formed between antenna and the mouth. The better coupling improves the signal discrimination by mouse pose changes. Okay, now we finalize the antenna configuration. These two antennas enhance the asymmetry for better sensing performance. We optimize the operating frequency, and our antenna is working from 2.2 to 3.4 gigahertz. This is overall hardware configuration. The final antenna is attached underneath the Meta Quest 2 headset, and it is connected to vector network analyzer to inject the signal and measure the signal. So how good is our technique? We conducted user study to address critical questions on feasibility and accuracy across two different application contexts. One, facial expression. Two, speech mouse movement. We recruited 12 participants. We used vision-based method for our ground truth data collection. In wearable, repeatability is important, so we included that factor in our user study. We collected one data set and completely removed the headset, and then we collect the validation data set. This allowed the comparison between performance drop-off when headset is reworn. Here's a diagram of 10 facial expressions that we investigated. And here's the result. For within one session, the tracking is within 1.9 millimeter precision, which is very accurate. If user rewear the headset without calibration, the tracking accuracy is 2.8 millimeter, which is still very respectable. If the specific user's training data is not in the training set, then the accuracy drops to 6 millimeter error. These are speech mouse the tracking accuracy result. Quite accurate, around 2 millimeter of tracking error overall. So despite respectful accuracy of Pantoena, there is a limitation. To achieve universal model for across user, the better software algorithms such as few-shot learning would be expected in calibration step to compensate various individual differences in facial geometry and bioimpedance. Next, an antenna-tilted radiation beamforming can allow the even thinner form factor and robust sensing. And we did not explore the reflexive signal from the second antenna because our off-the-shelf VNA does not provide it. But if we can use this signal, then the sensing can be more robust. And I also mentioned the faster VNA sweep would be required because in our paper it was 10 FPS, but I already improved that with different hardware. Now it's around 25 FPS. Okay, so thank you so much for attending our talk, and I'm happy to take questions from now.
First question.
Thank you for the great talk, Eiji Hayashi from Meta. And I actually have a question about the specific choice of the frequency of your system. So your choice of frequency is 3 gigahertz, I guess. What's the rationale behind it? And then if you change it, what kind of effect it could have? I can imagine that higher frequency may have a better result, but I want to ask for that.
Yeah, actually, that's really great intuition. So we already investigate the frequency range in our, I hope I can show you the slides because it's easier to understand. Okay, I think it's here. So this is the frequency response from...
It's not showing the result.
It's not displaying.
Oh, it's... Ah. Oh, I'm sorry.
Dewa will show you a frequency. Okay, there you go.
So this is the frequency response that we investigated, and around 2.5 gigahertz or over even higher frequency has more better discrimination. So your intuition was correct in our simulations.
Yeah, and I can imagine that the 60 gigahertz data is available off the shelf, so it may be interesting to try it out.
I see. We didn't investigate it because our VNA only support up to 4 gigahertz, but if we have those hardware, then it would be interesting to investigate.
Thank you.
Next question.
Thanks for this amazing demo. Really cool. Could you detect the position of the tongue for some kind of hands-free, invisible interaction?
Oh yeah, that's actually interesting question. So in our demo, in our pipeline, we already tracking the tongue tip position right now. So we think we can validate it's possible to track the position. But with the closed mouse, because we are using the higher frequency range, maybe it's difficult to use track the position of the finger tongue tip at this point. But if we can explore the lower frequency, then maybe it's possible to, even though the mouse is closed, maybe it's possible to track the position.
Thank you.
Let's thank our speaker one more time.
Thank you.
And that concludes this session. Thank you very much for attending. And if you have any further questions to the authors, they're going to be here up front. So thanks. And I think Vision's talk is also going to be in this room. So see you in a few minutes.